Nowadays, everybody heard the term artificial intelligence and how training the machines changing our lives. Depends on our field and career, AI evolves more or less in our everyday lives. And companies are looking more and more to find experts in this field. Are you an engineer, a business analyst, a researcher, a student, or even an enthusiast that want to be an expert in machine learning and data science and secure your future job in top companies? Are you the one that always afraid of programming and mathematical equations? My name is Navid Shirzadi and I created a course named Machine Learning and Data Science from A to Z. In this course, you will get more than 14 hours of on-demand content and learn lots of required items that you need to know as a data scientist, such as pre-processing of the data, visualization of the data, development of machine learning models, and also at the end, tuning those models. This course is the product of several months of hard work to make even the hardest mathematical equation into something completely understandable for all of you with any kind of background. Are you ready to start this journey with me and be one of the future data scientists? Let's start today. Here you just type Spider, and you can just type IDE as well, Spider IDE. So the first website that will appear here is the Spider IDE website that it mentioned, spider-ide.org. So just open it up, and here the Spider website will pop up, and from the tabs, the upper tabs, you can just click on the download section, and it will go straightly to the download section and refer to your, based on your operating system, it will bring up the download file for you. For example, I'm using Windows right now, and here I have the download section for Windows. If you're using Mac or other types of operating system, you can just download the version referred or based on your operating system. And if you click just on the link, download link, it will automatically start to download the executable file, an executable file for you. So I will just pause here the video and we'll come back after this downloading finished. It's not a very big file, but it takes some minutes, and then we will come back for installation. Okay guys, the installation is finished, and now by clicking on the executable file that is downloaded here, the installation process will just pop up. Yeah, that's it. And then by clicking the next, it's very simple and straightforward. Just click next, agree. You can choose both of these terms on your computer or just for you. And I go with default for the destination folder. You can change this, and just by clicking install, the installation will be completed, and you may need to restart your computer, and then you will come back to your Windows. I don't do the installation because I have it already in my system. So just by clicking in here in the, if you're using Windows, in the search tab, just by typing Spider, you can find out the this Spider executable file in order to go to the Spider. So it's very easy. In the next tutorial, we'll come back with how to install the required packages or libraries for what we want to do with machine learning. And yeah, that's it for this section. Until then, enjoy using data science. So in this section, I want to tell you how to install the required packages because before we go to the Spider environments. So I know these terms are a little bit frustrating right now: NumPy, Pandas, Matplotlib, scikit-learn. If you haven't heard about them before, but don't worry, we will go through them one by one, these packages, and I will tell you everything about them, and we will go deep into them and to find out the even the tiniest things about them. So in this section, we just want to install them before we go to the environment. So just come along with me, and then in future we will talk about each of these packages and libraries. So these libraries, we can install them in two different ways. We can use pip installation, or we can use Anaconda distribution installation with the code conda installation. But as we are using we are not using Anaconda in this course, I want to go and show you how to use pip installation. You don't need to have Anaconda for the pip installation. So it's very easy. It's part of your operating system. Just let me go through my windows here and type cmd. By typing cmd here, this will pop up as the command prompt. Just right click on that and click on run as administrator. So cmd command prompt run as administrator. So by clicking on that, this dark area will show up. It's not very difficult. From now on, you should just type some lines. For example, we want to install NumPy, so I should say pip space install space NumPy. So if I click enter, it will automatically start gathering the package for me. But as I have this package in my system, it will tell me requirement already satisfied. But for you, it shouldn't be like that. It's starting downloading the NumPy package for you, and at the end, it will give you a successful message that okay, this package successfully installed. So this is what you should do. Just type pip space install space NumPy, and the second one is pip space install space pandas. It's very easy. It's not very difficult. Just by clicking enter on your keyboard, it will try to install. Again, I have the panda, so it's telling me requirement already satisfied. But for you, for sure, it will go and gather the package from the internet. And the next one is the scikit-learn package. So we write again pip install, sorry, and here we use a dash and u, and again space. Here we just type scikit-learn. Okay, scikit underscore learn. So by pressing enter, it starts to gather the information. As you can see, it is requirement already satisfied, but it can, in order to update some of my packages that is not there, I have, for example, installed it a long time ago. So it start to collect some of the parts again. So as you can see, you should see something like this: collecting scikit-learn, downloading. So it start download all of these packages for you, and then at the end it mentioned that successfully installed scikit-learn, the last version that it has. So it's very easy. Just again, we'll go through it: pip space install space dash u space scikit-learn scikit underscore learn. So, and the last package that we are going to use in this uh, course is the pip install is the scipy package. So we just say scipy, and it will start to gathering, but for me it's already satisfied. So for you, it should just go through this just like this, downloading the scipy package for you, and then in the end it should give you the successfully installed scipy the version. And also I forgot to install the Matplotlib, another visualization, good visualization package. So let's do this with together. It's pip install Matplotlib. So just by entering here, it will start to gather the information for you. For me, it's already satisfied, but for you, it will gather the information. So that's it. That's all the packages that we needed. Let's go through them very fast again. In pip space install NumPy, pip space install space pandas, pip space install space dash u space scikit-learn underscore learn, scikit underscore learn, sorry, and pip on space install space scipy, and at the end pip space install space matplotlib. So we have installed the required packages that we needed. But in the future, if you wanted, for example, you're working with another libraries that is out of the scope of this course, and it's just the same process. It's not very difficult. Just come here and type cmd, open your command prompt window, and here just type pip install your package that you want. You can just Google it in the internet to find out what is the exact line of code that you should write here for installation with the pip. But usually it's not very difficult if you just mention pip install and the name of your package, and the pip installation will done automatically very fast, and it will download and install it for you. So it's very easy. Do not it shouldn't be make you concerned about this. So that's it for this section of the tutorial. In the next tutorial, we will talk about the Python interface and the Spider interface actually that we downloaded and installed it together. Until then, enjoy data science. So in this section, it's very interesting. We have opened up the Spider that we downloaded and installed. The first thing that appears should be an environment like this. If it's not, we can change it. Don't worry about that. So you have different sections here. We have a part that we can type and type our code here. And we have the console here that shows our variable explorer, help, file, profiler, code analyzes. And we have also our console here that shows the results and these things. We'll talk about it soon. But first of all, let's go through the interface very fast. So from the tabs here, just click on Tools and go to Preference by clicking on Preference. This window will appear. So in the preference, you can first actually go to appearance, and in the appearance part, you can just change the interface theme very easily by clicking on this. If you like the dark mode, I would prefer the light mode, but if you don't like the dark mode, just click on dark and apply it. So it will change to dark automatically very fast. So it will restart my area, so I don't do that right now. So if I go to light again, so it's very easy. It's just restart your Spider, and then you will open it up again, and then it will be dark. Uh, you can change the style, you can change the icon theme, you can change the even the size of your coding here and the type of your coding. I will go with default, but if you like to have a bigger size for your codes, you can just change it here. This is all about the appearance and what you prefer. It's not very important to your code. Uh, Here we have an important things about the keyboard shortcut just after the appearance. For the keyboard shortcut, it can help you, especially in the future that you code too much. It can help you to save some times. So you have lots of keyboard. For sure, you don't have to remember all of these. But the thing that we have in this course, and I like you to change it right now because I use it very much, just click on the search and type run. So these are all the keyboard shortcuts for the running of different cells or your codes. So in a run selection, just click on run selection and change it to what is easy for you to remember. For example, I like F9 very much. So in the during the course, if I say press F9, I mean the run the selection. So if you like, you can just put it as F9. Just by double clicking on it, you can just press F9 now and press OK. If you don't, just click on, press any key on your keyboard that you are happy with it. You can remember it very much. And then press OK. And it will appear here as a shortcut for run selection. Because we use this too much, I just wanted you to be aware that when I'm saying F9 or run the selection, I mean this shortcut. So that's it. You can just change other shortcuts as well if you want by just double clicking on them and then pressing the shortcut that you like. But the most important one that I like to change here is the run selection part. And the last thing that I want to tell you about this preference section is the Python interpreter. So as a default, I imagine that you have Python on your system. If you don't, please go to Google, just type Python download, and it's a very open source programming language, and you can download it in the Python website. And it's very easy, very straightforward. Don't worry about that. Just go to Google, type Python download, and uh, download the last version of the Python. So because the Spider needs the interpreter means the core of the Spider. Actually, Spider is just an environment. It uses the Python as the brain of it. So just download the Python itself, and you can use it as a default, or you can use it here as an interpreter. You can just define it. If you have several types of versions of Python, you can just come here and select the Python version that you like here. So the Spider goes through that version as an interpreter. So I will go with default right now. So in the run, you can have several buttons to change. I don't want to go through all of these, but there are some things. For example, in editor, you can change some of these tabs by clicking on them, showing what to show and what not to show in your editor section. So that's it. That's for preference. And then if we go back to the environment, here you can save your file. Here you can open new file. Here you can open your previous codes and these things that we are using them very much during our codes. And also you have other buttons that we don't use too much, but this is for running all of the codes all together. This is for selection. This is for selection and going to the next cell, and it's better for debugging things. And we don't use these things, but we just use the F9 that I tell you so much. So that's it for the interface. It's very user-friendly and easy to learn interface in Spider. If you worked with MATLAB before, it's not a very different environment, so you will be happy with this environment as well. And we will talk about it more in a detail of coding in it in next tutorials. I just wanted to tell you about the interface very quickly, and we go through it with together very quickly. So that's it for this section. So in this chapter, we just want to quickly learn what are the types of machine learning models, and it's very easy and very quick. Don't worry. We will go through all of the types with together one by one. So as you may heard, the machine learning models are actually classified into different algorithms. And these algorithms are supervised, unsupervised, and reinforcement learning. So we have different types of learning algorithms in machine learning models. And these algorithms are, again, based on supervised learning, unsupervised learning, or reinforcement learning. What are these algorithms and what are these learning algorithms actually? If we start with supervised learning, let's say we have a bunch of cats picture, very beautiful, cute cats here. So we have a bunch of cats picture. Imagine that we have thousands of them, for example. I just brought 6 of them here. So these cats picture and also some cute dog pictures we have here. And we want to give these pictures labeled. So we have cat label, dog label, and give it as a training set to the machine or computer. What does it mean? It means that I'm telling my computer that Okay, this picture is a cat. This picture is a cat. This one is cat. This one is dog. And this one is dog. So I'm labeling all of these pictures as cats and dog, and then give this information, give these pictures to my computer to teach my computer what is cat and what is dog. So after this training, my computer will understand the difference between cat and dog by just these labeling that we have done. Why we are calling it supervised learning? That's because we are giving the labels. We are actually specifying the labels for the computer. So computer will understand this is cat in the initial stage and this is dog in the initial stage that is training. So the next step would be testing my machine, my model actually. And in this test will be, for example, I will give this picture to the computer and will ask computer to predict what is this picture. Is it cat or is it dog? So based on these trainings that we have done before in the training stage, the computer should give us the response, the prediction with a good accuracy based on these training in a testing stage. So it should give us that, for example, with 90% accuracy, it should give us sometimes maybe it has some errors, so it will give us the cats. But I want to just tell you what is supervised learning here. And if we review it again with together, uh, we will label our pictures. And these labeled pictures that these are cats, these are dogs will be given to the computer. And we will ask the computer the next to predict the next picture, and it will give us the response that is the dog. So this is called supervised learning. But what is the unsupervised learning? Actually, in unsupervised learning, as it is clear from the name, we don't categorize the label to we don't actually categorize the label the input. So it means that imagine we have a bunch of cats and dogs here, and they are not categorized. We don't label them. We don't tell the machine that which one is which, and we just give this information, give these pictures to the computer. And that's the only thing that we do. And the computer will actually categorize these cats and dogs into two separate groups, group one and group two for us. So this is called unsupervised learning. So based on the similarities that a computer find in these pictures, for example, this cat picture with this cat picture with this cat picture, it understands that these are in same category, and these dogs, because of the similarity that it can find, it understands that they are in the group two category. They are not in the same category. So actually this is unsupervised learning. We don't label anything here, and computer will actually categorize these groups for us. So this is unsupervised learning. And also we have another learning called reinforcement learning, that you have an agent or robots, for example, and you have an environment that, for example, this maze is our environment, okay? So your robots or your agent start from here, for example. So it has four possible actions to do: going up, going down, going left, and going right. Okay, so we have different actions that can our robots or agent can do. And then based on that actions, it gets to the end point. Okay, so imagine that, for example, it's here and it decides to go down. So based on this, it will go from this state to this state, and we will give it a reward or penalty. If it's the right state, we will give it a reward. If it's not, we will give it a penalty, and this will go on until the agent gets to the endpoint that we call this policy. So based on the actions and different states that it has, it gets a reward, it takes an action, and then it gets to the end. We call that policy. And actually, reinforcement learning is looking for the best and optimized policy for us. So this is called reinforcement learning, but it's not in the scope of our course. And in this course, we just cover and we go deep into the supervised learning and unsupervised learning, and we understand the concept. We'll go code some models and stuff for that. So that's it for this session. We just wanted to review the machine learning types and why we call them supervised, unsupervised, and reinforcement learnings. So in the previous chapter, we understood different types of machine learning models. In this chapter, chapter 5, we actually want to go deep into the supervised learning models. So supervised learning models are actually categorized into two main categories. The first category is classification, that we are actually dealing with discrete data. So if I want to give you an example, imagine that you want to, as a data scientist, you want to design an application for a medical team, and you want to actually, you have several options in front of you. For example, you can use binary classes or you can use multi-classes. What does it mean? The binary classes is exactly what we talked about in the dummy variables, if you remember, 0 and 1. So when you are dealing with actually just two classes, like true and false, like 0 and 1, that's binary class. And when you are dealing with the multiple classes, for example, it's not just 0 and 1, it could be 0, 1, 2, 3, something like that. These are the results. Still discrete, but it's not just two, it's multi-class. So, for example, for the medical team, you want to design a binary class application that can predict that the patient has cancer or not cancer. Or a multi-class that diagnose based on the symptoms. For example, based on the symptoms, the application can give you the disease that the patient has. So this is actually classification, and there is other category, important category that we want to discuss in future sections, that is called regression. That is when we are dealing with continuous data. This time it's not discrete data. So it's a continuous data. And I want to give you an example to understand what continuous data means. Imagine this time you are, as a data scientist, you are invited to design an application in order to predict the house price based on a different feature of it. For example, number of bedrooms, the location of it, and so on. So based on these features, you should actually develop a model that can predict the house price. This is called continuous data because you are dealing with uh, not just discrete, but set of continuous data. For example, for host number 1, 2, 3, 4, and thousands of hosts with different features. So this is the method. Now we should use the method that is called regression, and that's the other important category of the supervised learning. So for now, we want to start with classification. That's why I made it green actually. So for the classification, if you want to start, the example that we want to start with is the iris the flower data set. So that's why I prepared this slide to show you what is exactly the data set, and then we will go to the coding environment. So the iris flower dataset is an open source dataset made by a guy named Fisher, and it is called also Fisher's iris dataset. So this dataset is categorized into three main species based on the actually we have three types of flowers in this dataset. Three types of iris flowers. They are all iris flowers but different species. So the categorization is based on the uh, petal and sepal width and length. So based on petal and sepal width and length, they categorized, actually Fisher categorized the flowers into a three main category. And the dataset includes 150 50 samples, something like that. So 50 for each type. And these are the actually species that we talked about. Three main types of iris flowers. That one of them is setosa, the other one is versicolor, and the other one is virginica. And this is our data. This is what our data set look like. That has four features. That is sepal lengths, sepal widths, petal lengths, and petal widths. And these are our labels. So if we just concatenate these two together, let's name them again. These are our features, these are our samples, and these are our labels. So we call these features, we call these our samples, and these are actually our labels or targets. For example, you can see here that our sepal length is 4, our sepal width is 2, petal length is 1, and petal width is half, it's 0.5. So the type of this, the label of this is virginica. We are dealing with such a data. So if we go to our coding environment, Spider, okay, so it's fresh. We just opened up a new file with pressing this one, and I just renamed it Supervised Learning Classification, and this is our title. So let's start with Together Fresh. You just open a new editor for me. So here I want to start with the packages that we already learned. So maybe in the middle of the code we need them. So it's good to in the beginning of your coding, it's very good to import the related packages like NumPy, Pandas, and Matplotlib, because for sure we will need them. So for example, I want to start with importing NumPy just like before as MP, and importing Pandas as PD, and also importing Matplotlib dot pyplot as PLC. It's until now it's just like what we learned before. So we just typed three important packages that we learned how to work with, and in the first step I want to just select these and press run, and you can see these three packages imported successfully. So the next step is from the scalar datasets, we want to import the iris dataset. So iris dataset is an open source dataset. You can find that in internet very easily by Googling it, but the scale-learn dataset, in the scale-learn dataset, one of them is iris dataset. So we can import it from the scale-learn library as well. So we can say from scale-learn dot datasets import. So here we have several options. For example, one of the datasets that the scale-learn has is if you press just L, you can see that the datasets will be appeared. So for example, dataset load Boston, load breast cancer. We will work with some of these datasets in future sections, but just after this course, you can just work with these perfect datasets as and open source datasets as an exercise. That will help you very much. So for now, we are looking at load iris, okay, this one. So I click on this one, click enter. So we want to import load iris dataset from the scale-learn dataset subpackage, okay? So that's it. If I just want to say that, okay, iris is equal to load iris. So this is just to actually bring the data, the load iris data sets into the iris variable. So I want to make an iris variable so I can see it in my variable explorer. That's why. So if I select these two lines and press F9, you can see in my variable explorer now I have the iris. But what is this? Let's open it up and find out some information in that. If I open this up, you can see that we have several parameters here like DESCR, data, feature names, file names, and so on. So DESCR is actually the information of the data set. So we can find a complete information of this data set here if you are interested. For example, the number of instances, the 50 for each three classes. We discussed this mainly in our presentation, but if you like to go through that to find out more about this data set, this is where you should go. And also some information about the statistics of the data, for example, mean, max, average, standard deviation, and these things. So missing values, none, and it will give you very good information. So this is the first section, the SCR. And the main section that we want to work with is this one, that is data. So if I open it up, it's an array. As you can see, the type is array of float. And the size of it is 150, and with 4 features, 4 columns, 150 samples, 4 columns. You can see the size here. And this is actually our data. This is what we want to work with. 150 because it starts from 0, that's 150 data, and 4 features. And you can see even the feature names. For example, sepal length is 0, sepal width. So if I open both of them together, you can see that the 0 actually is sepal length, this one. 1 is sepal width. This one, 2 is sepal petal length, and 3 is petal width. So we will discuss this and we will make our data frame in a second. Just wait. And these are our feature name. I told you this is our file name. It's not important. And the other important thing is actually our targets. So this is the list of our target. Again, we should have 150 targets as well. As you can see, we have 3 main categories, 0, 1, and 2. And these targets, actually, you can find the target names here as well. The 0 means setosa, 1 means versicolor, and 2 means virginica, as we discussed in the presentation. So if I just close this, we went through review of our data set very fast together, and now I want to make my data set actually. To do that, I want just one thing before making data set. You can call any of these sections that we talked. You can call them one by one and see them in the console. For example, let me show you an example. I wanna from the iris that I just built it here. I want to call, for example, one of them feature names. Okay, so let's say feature. It was feature underscore names, I think. So iris feature names. I want to call this one feature names. Okay, so if I run this, you can see that in my console, I can see the feature names. That is sepal length, sepal width, petal length, and petal width in the centimeter unit. So that's how you can call each of the parameters that we talked about. And also you can say you can call other ones as well as an exercise for yourself. But the thing that I want to do is making my data set, and the first step to do that is I want to make a data iris variable and put the data, this one. I want to put this data into my data iris variable. So it's very easy. I should just say, like what I did in the above for calling the feature names, I should just call it. Here I should say iris dot data. Okay, so it goes to the iris, it calls the data, and it just copies it into the data iris variable. Very easy, very straightforward. So if I just select and run this, you can see that my data iris is now created. And it's the array of floats, and the size is 150, and we have 4 features. So it's an array. So let's change it to a data frame format. If you remember in the previous chapters, we talked how we can change an array to a data frame format with pandas method named data frame. So let's do that. I want to say, for example, my data iris is equal to pd dot what? As you guess, data frame. And inside of the parentheses, I should mention data underscore iris. Actually, this is the data underscore iris that I just made. This is the array that I have. I want to make it a data frame. And the columns are actually, what are the columns? The columns are, let's open this iris up. What are the columns? The columns are features name, or these sepal length, sepal width, sepal petal length, petal width. So very easily, I should just call the feature names. I can say iris dot feature underscore names, and that's it. As we called it here, we can just call it here and put it in the columns. So that's it. This is our code for changing our array that we just built here to the data frame. So let's select these two. Actually, we already did that. So let's select just this line and press run. And now you can see that the data iris data set is changed the type from the array to the data frame. You can see the other things are the same, but it changed the type. And you can see that it actually is a data set. It's actually in a data frame format because we have our feature names at the top, as you can see, and we defined it for it. So you can see that our 4 features, sepal length, sepal width, petal length, and petal width, and we have over 150 samples. This is the first step to make our data frame. The next step, I want to actually have my labels as well. I want to know what are the labels, and to do that, to adding the labels into this data frame that we just created, it's just very easy. So I use data iris. So you already learned this in the previous chapters as well. Inside of the brackets, I mentioned the label that I want to add. So let's call it label or targets or any name that you like. And this is equal to just calling the targets. So iris dot targets. If you remember, if we check it, check this again. These are our targets. Okay, we want to add this column to our data set and call it label or target or anything that you like. So if I select this and run it, and if I check my data iris again, you can see that the label has been added end to end. Okay, so now we have our data set and label, and we know that each label is refers to what samples. We actually labeled each of these samples that we had. So I think our data set is ready, but before we go through the modeling part and our first classifier model that is very interesting, I want to use the Matplotlib in order to visualize my data. That will help me to understand my data better. So to do that, just remember that because we cannot plot 4D graph, and it's not possible, I just used 2 of our 4 features because we had 4 features, if you remember. These are our 4 features, but I cannot plot all of them. So I used 2 of the features to plot the graph for it. So let's use, for example, a scatter plot. For now, I'm assuming that you know how to plot several graphs, scatter, line, histogram, bar plots, and bar charts, and several others. So uh, for now, let's go after scatter one. I know you know how to do that. So plt dot scatter, and as you remember, inside of the scatter, we first should define the x and y. So the x is actually our data set iris, and if you remember that we used iloc for our data frame in order to separate some columns. Let's open this up. For example, I want all the rows. But I just want, for example, column number 3, something like that. So to do that, if you remember, we were using the iloc method to separate that. So let's say I want to, for example, based on the petal lengths, I want to make my visualization. So I would say data.iris dot iloc, and in the brackets I mention all of my rows, and the column that I want to pick is actually let's say 2. Okay, so the other thing I should mention, I should specify the y as well. So the y is actually our labels. So let's go after. So sorry, the x is one of the so let's say, for example, here this is what we called the x, and the if I mention, for example, this one data underscore iris dot iloc, this time, for example, let's say all of the rows and 3, and this time I wanna have some labels. My labels are the colors. The color that I want to specify here is my label. So based on the color should be specified based on my labels. I have 3 labels that are different, different names of my flowers. As you can see here, this Setosa, versicolor, and Virginica. I want to classify these 3 based on the different colors. So I say color is actually iris dot target. And let's say plt dot x label is equal to, for example, the x label is petal length in centimeter. Oops, we should put this in the quotation, I forgot. So let's just copy and paste this, cut it here. And for the y label, I should say plt dot y label, and inside of the parentheses, inside of the quotation, I use petal width this time, and again centimeter. So this is my x label and y label, and actually my x is the petal length. So this is my x, and this is my y. Actually, I wanna, as I told you, I cannot do this for all of them. So I should just pick 2 of them as x and y. So I'm actually visualizing the petal lengths and petal widths as x and y, and I'm using labels as my colors. So this is number 2, as we mentioned this here. Petal length is number 2, so I want all the rows and number 2, that is 0, 1, 2. And I want for the Y, I want all the rows as well, and the number 3, 0, 1, 2, 3 petal widths. So that's it. And also at the end, we should say PLT show to render our visualization. So if I select these lines of code and press run, you can see that my visualization is like this. So this is a good visualization actually. So you can see the 3 types very specified by different colors. So you can find out we can find out which one is which by just labeling all of them. So for example, this is Setosa, this is vertical or something like that. But for now, I just wanted to show you that how these dots, how this data is look like. So you can see that even with the 2 of the features, that petal widths and petal lengths, we can categorize our data into 3 main category, and it's very obvious, okay? That's a part of understanding your data, and it can give you a very good overview about your data. And I strongly suggest to visualize your data in a pre-processing stage before going to the modeling. So now that we processed our data, and if more importantly understood our data, it's time to develop a machine learning model. So uh, it could predict and classify and label our next flowers. For example, you give your next flower data and it should predict for you. Before we close the pre-processing section, because we need to separate our labels features from the independent variables. So let's do that because we need this in our next stage, and I don't want to do that. I want to make everything perfectly prepared for the model. So what we need is to define X and Y. So the X is my data iris and dot ilog. If you remember from the data frame, we used ilog in order to separate what we want from the data frame. And inside of the brackets, I'm saying all of my rows and from 0 to 4. What does it mean? It says that, okay, from this data frame that we created, separate this line, this column, this one, and this one, these 4 columns. So this is 0, 1, 2, 3. But why we wrote 4, if you remember, I already explained this for you, that Python starts from 0 and ends not in a tree. If I mention 3, it ends in this column, in actually 2 column. So it actually, you should mention the next column that you don't want it, but it stops from the previous one. So when you want this, and this, that is 0, 1, 2, 3, you should mention 0 to 4, so it stops on 3. That's a Python trick that I explained it for you before, so I hope you remember it. So that's why data.iris.ilog all the rows, and from 0 to 4 it's our X. And I want this label column as my Y, okay? I want this label column to separate that as well, so I should say Y is equal to data underscore iris and dot ilog. What should I write? So just review it for yourself. I want this one. What should I write here? So I want, as you guessed, all the rows and which number? So this time my number is 0, 4, 0, 1, 2, 3, 4. So I want number 4. So I just put 4 here. So if I select these 2 of lines and run it, you can see that my X is actually my 4 features, and my Y is my label that I perfectly separate them with together. from together, and now it's ready to be used in our model. So in this session, we want to understand our first classifier or first classification model, that is KNN, or K nearest neighbor. In a second, I will tell you why we are calling it lazy learner. So to start to understand what is KNN and how it actually classify and how this model works, let's start with the graph that we actually visualize it at the end of the previous session using Matplotlib. So this is, as I told you in the previous session, we cannot plot a 4D graph. So just imagine that we have just two features, that is petal width and petal length. Okay. So as you can see here, our training set is has two features, petal width and petal length, and we have three labeled species of the iris flower. That this one is setosa, this one is versicolor, and this one is virginica. We actually know the labels of them, and we are giving this to our computer, to our machine, to understand them very well. So imagine that we gave it to the we have already gave this to machine, and machine trained, understand it, and you have one sample, and you want to give it to the machine so it can predict that this sample is related to which of these categories. Is it virginica, is it versicolor, or is it setosa? So let's say our point is this point, the petal length. You have the petal length that is 4.32 centimeter, and you have the petal width that is 1.68 centimeter. So if I visualize this here, you can see that this is our point, 4.32 and 1.68. So this is our point. How KNN acts here is, as you can imagine, we have it used the k number of neighbors around this point. For example, if I say k is equal to 1, it means that it draws a circle and it just consider the first or nearest, just one nearest neighbor. Okay, in this circle you can see that we have just one point. If I say k is equal to 2, it means that it actually goes further and it considers two nearest neighbor to classify this point. So it just draws this circle to have 2 points in it. And so on. If I say, okay, imagine that k is equal to 6, it means that it considered 6 nearest neighbors. So you have 6 of these points from your training set inside this circle. So it's very easy to understand the concept. So as the name is clear, k nearest neighbor. So for example, if k is 6, it means that it used 6 nearest neighbor in order to find out what is the category of this point. Is it setosa, is it versicolor, or is it virginica? So that's the concept behind it, and also why we call it lazy learner, because the method that it used in order to predict this and classify this point for us is in a lazy way, and it just look at the training set, look at the samples of the training set, and to find the best match. And that's the only way. It's not very complicated, it's the easiest way. That's why they call it a lazy learner. So this is the concept behind how KNN classify these points. And but the question that will be raised here is how actually KNN calculates the distance to find out the nearest neighbor. If you remember, we said that, okay, if k is equal to 6, it goes and find the 6th nearest neighbor around this point. But how the KNN calculates how it can find out which one is nearest. So it should go for distance. For example, say the distance between this and this is nearest, so this is the first point, and this one and this one. So this goes exactly for distance. So it uses exactly the distance in order to find the nearest one. But how it calculates the distance, if you remember from the normalization session, we talk about several distance calculation methods like Euclidean, like Manhattan. And I promised you that we will discuss it in future sessions, and this is the time. So Euclidean, let's go deep into it and find out how it calculate the distance. So Euclidean actually calculate the distance very simple by drawing a line connecting 2 points with. Consider that we have these 2 points, this blue point and this red point, and for example, we call this x and we call this y. And to calculate the distance between x and y, what Euclidean distance do is just drawing a line, straight line between these two, and calculate the distance. And the formulation, as you can remember from high school, it's very easy. It's SQRT of the summation of xi minus yi, x and y, in the power of 2. And that's very easy. And the other distance method is actually Manhattan method that we discussed it. It has other names too, like taxicab geometry, but I just brought taxicab geometry so you can, for example, if you saw this name, you can find out that it's Manhattan method actually. So Manhattan method or taxicab geometry method, it uses actually horizontal and vertical lines in order to calculate the distance. And unlike Euclidean, that was a line connecting, this time we have several horizontal and vertical lines. Something like this, for example, if I want to calculate the distance between this point and this point, it just use this horizontal line, this vertical line, and this horizontal line. So 2 horizontal and 1 vertical, something like that. So, and the formula for doing this to calculate the distance between x and y is summation of the xi minus yi, the absolute of it. So that's a very easy formula. And there's another distance calculation method that I want to tell you, and it's Minkowski method. And in the Minkowski method, it's very interesting. It's somehow a combination of the Euclidean and Manhattan method. So you can see that in the formula, the distance between x and y is equal to summation of xi minus yi, but this time in the power of p, and the whole formula in a power of 1 divided by p. So the interesting thing is, in this formula, if I say p is equal to 2, just imagine that p, that we call it norm, is equal to 2. So we have the formula changed to this formula actually. So because we have the whole summation is in the power of 1, is in the power of half. So it means that we have a SQRT of this summation, and this is 2 exactly like this. So if the p is equal to, the formulation is exactly the Euclidean method, so we have Euclidean. And if p is equal to 1, as you can guess, if p is equal to 1, the formula is changed to this formula, it's exactly this one. And we are actually using Manhattan method. So the Minkowski is actually something between these two. And we typically select p something between 1 and 2. So if it's 1, it's Manhattan. If it's 2, it's Euclidean. And if it's between 1 and 2, it's something different from Euclidean or Manhattan that we call it Minkowski. So that's 3 main methods that Canaan use in order to find the nearest neighbor of that point that you want to predict. I think now you understand the concept behind how KNN or K nearest neighbor works and why we call it lazy learner. And in the next tutorial, we are going to develop our first model in the Python that will be very interesting. And I'm very excited to start that tutorial. So until then, take care and enjoy using data science. So now that you understand how KNN works and what is the concept behind KNN, let's code our first model in machine learning. The first step, as usual, is importing the related package of KNN from scalearn. So let's do this with just one line of code. We say from scalearn that this time I want to use the subpackage neighbors. You can see the different subpackages that scalearn has. So we want to use neighbors this time. And I want to import a method from the neighbor subpackage that is called k neighbors. You usually get the suggestion, but sometimes it's not very fast. So you can see the different suggestions I have here: k neighbors classifier, k neighbors regressor, and we want to start with k neighbors classifier because we want KNN classifier actually for the classification. So from the neighbors subpackage of a scalearn library, I imported kneighbors classifier as a first step. Now it's time to train our model first. We call this stage actually fitting. So let's say I wanna make another variable named k and n. Okay, so I want to put my model into this variable. So let's say I'm using this method KNN classifier that I just imported. So let's say k neighbor. Just you can copy and paste this or just use a suggestion. And inside of the parentheses, I should mention several parameters. If you don't remember it, just press Ctrl I and go to the help section to find out what are the exactly parameters that we need to identify here. So the first parameter, as you can see here, is the n neighbors. If you remember from the presentation, we discussed the k that we actually should define how many k we have. This is actually the most important part of the KNN is defining this parameter. In the future session of this course, we will talk about how we can optimize this parameter, but in the first step, we should define that. So the default is 5. So if you don't specify it, it actually goes after 5. But let's say we want to, for example, have 6k. So let's say our n underscore, just you should write something like this, n underscore neighbors. So n neighbors is equal to 6, for example. Okay, so this is the first parameter. The second parameter that I want to discuss here that and is important for us, for example, is the metric that we want to use. If you remember the metrics, actually the distance, that the different distance metrics that KNN use, and we discussed it in the presentation, and we went deep into that, like Euclidean, like Manhattan, Minkowski. So in case the default is Minkowski, so and with the p is equal to 2. So when p is equal to 2 and the metric is Minkowski, if you remember, it was using actually Euclidean metrics. And if p is equal to 1, it was using Manhattan metric. So let's say we don't want Euclidean, we want Manhattan. Let's say the metric is equal to, here I should mention Minkowski. So let's say Minkowski. And out of this quotation, I should mention the p. So p is equal to, you can see that the p is default, the default parameter for p is 2. So I don't want Euclidean, I want Manhattan, so I should mention p is equal to 1. So let's review it again. We first define the first parameter that is the number of neighbors, the k number of neighbors. So we define it as 6. If you don't define that, if you don't specify that, the default is 5. And the metrics that we went for Minkowski and p is equal to 1, that means that our metrics is actually Manhattan distance. It used Manhattan distance in order to find the 6 nearest neighbor to our points that we want to ask our model. So these are all the actually the parameters that I want you to remember and define for your model. And so now that we actually specified our parameters, I use X and Y that we defined in the pre-processing section to fit my KNN classifier on them. So if you remember, these are the X and Y. If you go to the variable explorer, you can see that the X actually are our data, our features. If you remember, it was sepal lengths, actually sepal widths, petal lengths, and petal width. So these are our features, these are our data that we want to fit. And Y is actually our labels that shows each of these samples refer to what type of flower. Is it setosa, is it virginica, or versicolor? So based on these 3 labels. So I want to fit these data on my model. So my model will be trained with these X and Y, so it can predict for me in the future. So the next step is I should say this this variable that I just made, k and n, and I want to fit my data on it. I say very easily use fit, and inside of the parentheses you should just mention your X and Y, your data and your targets. So my first is X and the labels are Y. So my features are saved in X and my labels or my targets are saved in Y, and we did it in a pre-processing stage, if you remember. So that's it. That's actually it. Congratulations. Our model is ready, and actually our first model in this course, machine learning model, has been made just by these 3 simple lines of codes, and for sure the pre-processing stage. And now that we developed our model, we need to predict with that. First, let me just select these 3 lines of code. So we will be sure that our model is working and trained. So let's press run. Now, if you don't get any error and at the end you see this line here in your console, that means your model actually trained by 6 number of neighbors and p is equal to 1 that mentioned it uses the Manhattan distance for the as the metric. So that means that the model did its job. So now it's time to predict with that. So to do that, for example, imagine that someone gives you a sample that contains sepal and petal widths and lengths, and he or she asks you to what is the type of this flower. So with your model, use your model and give me the type of this the flower that I just measured the petal and sepal widths and lengths. So let's say, for example, our new sample is x new, and this is equal to an array np, that's array. Let's make an array, sorry. And in this array, in the parentheses, I have 2 brackets, if you remember, and I just want to make a simple array by petal and sepal widths and lengths. So let's say let's open up the X so you can find out the order. So the first one that I should mention is sepal length. So imagine that my sepal length is 5.6, the new sample, comma, and the next one is sepal width. Let's say our sepal width is, for example, 3.4. And the third one is petal length, and let's say our petal length is 1.4, and The last one is petal width that, let's say, it's 0.1, something like that. So this is our new sample that actually somebody gave it to us, and or we measured it ourselves, and we want to find out we want our model actually predict what is the type of this flower. Is it setosa, is it versicolor, or is it virginica? So if I just select this line and run it, so I can make this variable x underscore n. So you can see this is our new sample. So I want to give this to my model to predict for me what is the type of this flower. So to do that, it's very easy. We just used our model that we just fit our data on it. So we say KNN. This actually shows your model, this KNN. And now you want to predict with that. Dot predict, very easily, very straightforward. And inside of the parentheses, the only thing that you should mention is the sample that you want to find out the prediction for that. So our sample is x underscore n. So we actually are asking our model KNN to predict the xn, this array that we just built, this sample for us. So if I just select this and press run, you will be surprised that, yeah, that's it. In your console, you can see that we have 0 as a result. What does this 0 mean? Let's go again back to our data, the iris data that we imported. And in the target names, you can see that the 0 is referred to setosa. So this means that actually this sample that we just entered is predicted by our model as setosa category. So let's do another thing. Let's give our model another sample so we can find out if it can predict it well or not. Let's say our second one is x and 2, for example, and it's equal to, again, as you guess, I want to make an numpy array. And inside of the parentheses, I want to mention 2 brackets, and inside of the brackets, okay, so you know the order now, but let's open up this x again. So the first one is our sepal length, that is 7.5, for example, and the next one is sepal width, that is, for example, 4. And the third one is petal length, that is 5.5. And the last one is petal width, that is, for example, imagine this time a little bit bigger, 2. Okay. So we have another sample with these numbers for sepal and petal widths and lengths. So if I just select this and import it to my variable section, so you can see that I have x and 2. This is my sample. And if I say ask my actually KNN classifier or KNN model to predict this time for me, this time x underscore n2 for me, and if I just select it and run, you can see this time my model telling me that this time this sample is referred to label 2. So what is label 2? Again, let's check target names. You can see that label 2 is refers to virginica. So the first one predicted as setosa, the second one predicted as virginica. As an exercise, just go ahead and give it some examples. Give the model that you just developed with me some examples and some samples in order to find out what is the category, what is the type of your flower that you just entered. That will be very interesting because this is your actually first machine learning model, and your model is doing a very great job for you. So in this session, we want to understand how we can test our models or classification models. And to do that, we actually need to make our test data set. So how we can do that, how we can make our test data set. Imagine that this is, if you remember, this was actually our data set that we trained our model with. It has 4 features: sepal length, width, petal length, width, and also we had 3 labels, 3 targets for different flowers, if you remember. 0, 1, 2 for Setosa, versicolor, Myginica. So this is actually our data set. And what we want to do is actually randomly select some of these samples. Imagine that it could be 10%, it could be 20%, 30%, so any number that you like and you think it's enough for you. Imagine that, for example, 20%. So we want to select randomly 20% of this data set and extract it from our initial data set and put it in another data set, another smaller data set like this that contains all of our features and also our labels. So this is what we called actually our test set. What we're actually doing is imagine that you randomly selected 20% of your data set, and here we have a 20% of our data set. So what remained here is actually 80% of our data set. So we have 80% of our data set in order to train our model, and we have 20% of our data set here in order to test our model with. So very easily, we just randomly select 20%, so 80% we train. With that 20% that we just randomly select, we test our model to see how good it is. So let's go to the coding environments and see how it is actually done in our model. So if I go back here, if we want to start with that, so there is a special package for that in sklearn in order to split our data set into a training and test set. So to do that, I want to actually first import the method. So from, let's go a little bit down, from sklearn again. So you see this sklearn library is a very useful library. We can use it very much in our models. So from sklearn dots, this time I want to use the model selection subpackage. Model selection, you can see that the suggestion will pop up. I use that from sklearn dots model selection. I want to import actually train test split. So let's just write down train test split, and you can see that the suggestion will pop up. So actually, I want to use this method, train to split. The name is actually clear that we want to split our training and testing set. And I want to import this from the subpackage model selection from the sklearn library. Okay, so that's the first stage. Let's select this and import it. Perfect, it is imported now. And now we want to say, okay, so now that we imported our method, I want to use that. So this is an important part. So listen carefully. I want to say import actually, I want to have xtrain, like just like what we have here, x and y. Remember, this was our x, and this was our y label. Okay, so we want to have actually x train and y train, x test and y test. Okay, so to do that, the order is very important. So this is, for example, I want to say the name of this is x train, and I separate it with comma, and I say x test. Let's put in a space here, x test, and use comma, and again y train and y test. So these names are not important. You can say, for example, any name. You can say x, you can say x train 3, something like that. So the name is not important, but the order is important. The order is, the first thing is your x train data set. The second one is your x test. The third one is y train, and the fourth one and the last one actually is the y test. So this order, just remember the order, but the names are not important, any name that you like. So after this, I want to say is equal to, I want to now use this method that I just imported, train test split. And inside of the parentheses, I want to mention some parameters. So the first parameter that you want to mention is actually, let's see, I just pressed Control I to see what are the parameters that I want to enter. So if you don't remember it, you can just come back to this one. So the first are the arrays, or the actually your data set. So the first thing is X and Y. Okay, so my data set includes X and Y before. Now I want to split this X and Y, this X to X train and X test. I want to split this Y to Y train and Y test. Okay, so this is the first step and the important one. And the others are, for example, the other parameters, you should specify the test size and the train size. If you remember in the presentation, I told you it could be 0.1, 0.2, 0.3, any size that you like. So, for example, I want to say my test size is underscore size is equal to 0.2. And if you don't mention the train size, it's okay, because Python actually understands that if the test size is 0.2, so the train size will be 0.8. So, but I wanted to mention it here so you don't be confused in future. So the train size actually here will be equal to 0.8. And now I want to just put comma here and go to the next line so we can see it here. The other important thing that I want to mention here is another parameter that is called random state. You can see it in the parameter section here as well. So this actually, I will tell you what is this. First, let's specify that. So let's say random underscore state is equal to, for example, 88, any number. So what is this random state? The random state gives you this opportunity. So if you come back and use these numbers, use this portion, this training and test set, same data will be selected for you the next time as well. So it is very important to set a number here. It could be any number, so it's just a code to your splitting. It's not important what is the number, you specify that. And if in future you want to compare your results, our results actually with we have with the option of receiving same same test set, you should have this number, because it goes randomly through your data set and actually split this. But if you specify a random state here and number a code for it, so the second time that you want to have the same thing and use the train test split, if you use this random state, and if you even use the other parameters, for example, the test set is 0.3, something like that. So it goes for the same splitting strategy. It goes for the same random. So it means that you can have the same testing and training sets anytime that you come back. But if you don't specify this, anytime you get different set of test and train set. So that's very important to remember. And I want to mention that the shuffle is true is equal to true. So the shuffle is equal to true, and because I want to shuffle it for me, I don't want to just select my tests, split my test and train from one section. And the last one that is, I think, again, very important that I want to specify here is, let's again go to the next line. I want to mention that the stratify is equal to actually y. What does it mean? So here you can see the stratify parameter. It defines it as well. Data is split in a stratified fashion. If you say yes, and if you don't want it, you can just mention the default is none. So if you don't mention it, it doesn't go for stratify. Stratify is equal to y means that the 0.2 portion that we just specified for the test set and 0.8 that we specified for the train set will be followed in all three labels. It means that the test set includes actually 0.2 of the label 0, 0.2 of the label 1, and 0.2 of the label 3, because we don't want to actually, we just want to have, let's check the labels. We want to have from all these labels, we don't want our labels, our test will be just from Satosa, okay? We want to have from all three flowers the samples for the test. So this is stratify equal to y is actually gives you this opportunity to have your test set selected from all different labels, not just from one or two labels. So that's it. I think now we are ready to split our data set. Let's see if it works. So if I just select this two lines, I just imported my library. So I just want to select my these three lines that I just coded. So if I press run, oops, you can see we have an error here. Train test split got an unexpected keyword argument random state. So it has a problem with random state, and that's the typo that I just had again. So it's random state error. So if I delete this and put random, you see dealing with Python's errors is not very difficult. It exactly actually gives you the error that where is the error, go and just revise it. So if I now select my lines and press run, you can see that it actually runs successfully. And you can see in Variable Explorer, now I have my X test, X train, and Y test and Y train. If you want, you can just open it up. You can see that they are same data set, X train, X test, but the X train is actually have 120 data, but the X test, look at the size, is 30 number of samples. So this is why we actually defined the 0.2 for the test set. So that's why our test set includes 30 samples from the 150 samples in overall. So we have the same thing for the Y test. Y test is this, and you can see that we selected some of the labels, and here is our Y train. And you can see again the Y test is 3, the size is 3 sample, and the Y train is actually, we have 120 number of labels here. So that's it. We have done our job here in order to split our training and testing set, X training test, Y train, Y test, and we built that. The next stage is actually this time just copy and pasting these lines. I want to just copy and paste these three first lines that we coded with together for the KNN. I just want to paste it here, okay? So let's say this time, as you imagine, the first two line is just as same as before, and the one that I want to revise here is this. Actually, we want to fit our model not this time on X and Y, but this time actually on X train and Y train. So we want to actually train our model with the training sets that we just splitted. So let's say X train. I want to train my model with 80% of my data sets. So it's X train and Y train. And I want to test it in future. So let's first train my model with these two data set that I just created. So I press run. And now you can see that without any problem, my model is created and fitted in my X train and Y train. Now that we trained our model with the X train and Y train that we just split it, 80% of the data. Now we want to test it with 20% of the data that we just extracted from our data set as a test set. So the only thing that you should do here, it's very easy and straightforward, just like before, just like what we did here, if you remember in Canaan that predict, just we give it a sample, just one sample. This time the difference is we have 30 sample as the test set. So let's say our KNN dot predict, and inside of the parentheses, I want to mention not xn that we mentioned here this time. As you guessed, I want to use x test. So I want to say x underscore test. So now I want to predict, I want to ask actually our model that we just built and trained with X train and Y train. I want to ask it to predict the X test for me. I'm giving the X test, and I know the Y test. I know that these are the actual results. Okay, this is the beauty of this. I know the Y test results, but I want my model to predict this so I can compare it with the actual ones. So let's say I want to just select this line of code and press run, and you can see that in a console it will appear. Let's say I want to put it in a variable name because I want to see it in my variable explorer. So I want to put it in variable name predicted underscore type. Okay. So the predicted types, if I just select this and run it again, you can see that another variable comes here. So these are my predicted types. So if it just visually, we can just compare this with the actual values. So we have actual values here as y-test. We know that this should be the result. And this is the result of our machine that we just developed our model and trained our X-train and Y-test. So as you can see here, just by looking at the results, you can see that the machine actually goes pretty well on some of them. For example, this time it has an error, but this time is good, this time is good, and so on. So it actually predicts some types for us, some labels, and we can compare it with actual values that we have. This is the beauty of using train test split, that we just splitted our data set into a test set and training set. So we can train our model with the training set, and we can test our model with a test set and compare it with the actual results that we already have it. So we know how machine is good or how bad it is. So in order to just, because in the future sessions, we are going after the model evaluation and how our model is good, how much is good or how much is bad in the last session of the classification tutorial. But until then, we want to actually give a score, give some score accuracy to our model with a very simple accuracy metric that we want to just use here. So let's say I want to use a metrics method from the scale-learn. So let's say from scale-learn, just import metrics. Okay, so let's import this, and yeah, it is imported, and I want to give the accuracy to my model, how much it was accurate actually with this procedure, with this training and testing. So I want to say the accuracy underscore score. I think it's right, yeah. And this is, and inside that parentheses, I want to mention the y-test and the predicted underscore types. Okay, so what I'm saying is actually I'm using one of the packages of sklearn, sub-packages of sklearn and metrics, and I want to use a method here named accuracy score, and inside of the parentheses, what should I specify is just the y-test that we actually have, our actual values that we have here, and our predicted value, not values, types, our predicted types that are here. So I want to mention my actual types and predicted types so I can compare. So this accuracy method score can compare these two together and give us a number. It will give us a simple number so we can find out how our model is good or how is bad. So if I select this and run it, uh, okay, so we have an error here. So we can say uh, the problem here is actually we didn't import the metrics that we wanted first. So it is mentioning that the accuracy name is not defined. So what is the problem? So here I think my problem here is I should mention the score. I think I should import it from here. So let's say from accurate scalar.metrics, we want to import, I think this is the problem. I forgot to, yeah, accuracy score. So sorry, I did it wrong. So sometimes you made a mistake in your code. So I want to import actually accuracy score from the accuracy score method from the metrics subpackage of the scalar. So that's the good way, just like what we did here for our, for example, importing the can neighbors classifier. So if I run this, select this line again, now we have our accuracy score method. And if I select this line and press run, you can see that in the console we have a number. So it's 96% accuracy. That shows our model is actually working pretty good. So with 96% accuracy, as I told you, we will go deep into the how we should evaluate our model in the last session of this tutorial, the classification tutorial. But for now, we just want to find out a very simple accuracy method, accuracy score, and give a score to our model that we just built together. So that's 96%. You can work with this number of neighbors as an exercise. For example, let's say this time I have, let's do it together just one time. Let's say, for example, I have 50. Let's make it very big. So if I just select this line of codes and press run this time, you can see that the accuracy here in a console drastically decreased from 96% to 86%. That means that if you remember in the intuition that we mentioned that the number of neighbors shouldn't be very big or shouldn't be very small, and it should be something in between. And that's why we don't use number of neighbors in a very big scale. So you use this. Actually, you change this number of neighbors and some of these metrics. For example, you can say this time I want to use the Manhattan or Euclidean, change with these two metrics and find out what will happen, what is the impact on your accuracy scores in exercise. That will be a very, very interesting exercise, so you can find out how you can improve the accuracy of your model, how you can increase it, how you can decrease it, and that's it. So we learned lots of things in this session, I think, and in the next session we are going after different types of models like decision tree. And until then, keep on exercising and enjoy using data science. So in this session, we are going after understanding the concepts of a very interesting classifier that is called decision tree. So imagine that we have a tree here. As you all know, the tree created from roots, branches, and leaves. So imagine this tree is an upside down tree. Now we can understand our decision tree algorithm better. So here we have a root. So for sure we have a root node for our decision tree algorithm. Here we have some branches that connect the root actually to our leaves. So we have leaf node here as our decision, and we have branch node. So you can see that this is actually the simplest way to introduce the decision tree algorithm. So we have a root node, just like an upside down tree. We have branch nodes, these branches, and we have leaf node. Okay, so if I want to make this a little bit with more details, so I just delete this one and make it like this. For example, this, imagine that this is our leaf node as a decision. So we have some nodes, some other leaves in between. So we have a leaf node here as a chance, another leaf node here as a chance, and at the end we have our leaf node as decision. So this is actually the concept behind the decision tree. It is just like an upside down tree, as you all know. So it has roots, it has some branches that includes the leaves as well. So, and at the end we are having our end leaf that we call it decision. So it may be a little bit confusing right now for you, but if I go to the example in the next slide, it may be more clear. So let's say this is our example, and you want to buy a house. You want to purchase a house, and you have some limitations for yourself in order to purchase that house. So what you create in your mind is actually a decision tree. So let's say you start with a question that where is the location of that house, that specific house that you have in your mind? Is it in downtown? So if the answer is no, it creates another question for you immediately. That is it? It's not in downtown, but it is. Is it very far from downtown? And if the answer is yes, you immediately uh, conclude that you don't want to buy that house. Don't buy that house. So this is one of your limitations that you have, that if the location is not downtown and it's very far from it, you don't want to buy that. So that's the first decision. So this is as you can see, it was exactly like what I told you. We have a node, root node. We have some in between leaf, like that we call it chance, and we have at the end we have a decision leaf that you can see it as a don't buy. So this is a decision. Let's complete this algorithm together. Let's say, for example, here in the very far question, the answer is no. So it goes to this question. Is it a 2 bedrooms? So the answer is no, but it creates another question for you. So is it 2 bedrooms home? So the house is 2 bedroom or not? So if the answer is no, it again creates the decision that you don't want to buy it, so don't buy. But if it's yes, this time it actually goes for buy decision. What if in the root node the answer was yes, it's in downtown? So let's see what will happen. If it's yes, it creates another question that is different from the no, actually chance no, or no branch. So here we have a yes. So we have another question created that is about the age of the building that you want to purchase. Is it new? So if the answer is yes, it immediately goes for buy, because it actually satisfies the root node that is in downtown, and also it's new, so I want to buy it. But if it's no, it creates another question, that is it less than 2 years or more than 2 years? If the answer of less than 2 years is no, we don't want to buy that, because this is another limitation for us, that we don't want to purchase a house that, even if it's in downtown, we don't want to buy it if it's more than 2 years built. So if it's no, we don't want to buy it, and if it's yes, we want to purchase that. So now our decision tree somehow is completed. So this is how decision tree will works. Actually, we start with a root node, and we have in between some leaves that we call them chance, and at the end we have some decisions nodes that we call, and there are another leaf node that we call them decision nodes actually. So that's it, and in the next session of the decision tutorial, we actually develop the model of the decision tree on our iris dataset, and that will be very, very interesting. So until then, enjoy using data science. So in the previous session, actually, we talked about the concept behind the decision tree algorithm. And now that you are familiar with the concept, let's go ahead and actually develop our model for the iris flower data sets right now. So for the first step, as you can imagine, we want to first start with importing the related library. Just for your information, the model is completely similar to, the process is completely similar to actually what we have done before for the KNN. So if you remember, we just imported the method from the scale on neighbors. This time we want to import another method. This is decision tree method from another subpackage of a scalar. And then the process is same. We'll go through it. We first create our variable, then we fit our data on it, and then we predict with that. We predict with the actually developed model. So to do this, just the first step is just importing the related method. So we want to import from scalearn. That this time we want to use tree. Okay, so from scalearn, the tree means the subpackage tree of the scalearn library. So we want to import, what do we want to import is the decision tree classifier. So you can see the suggestion. So we actually imported the decision tree classifier, like exactly what we did for k-neighbors classifier. This time we import decision tree classifier from the tree subpackage of scalar. So, and also I want to import the same from scalearn metrics. We have done it before, but I want to do it again. So we start actually our codes again. So import accuracy, just like what we did for the KNN in the last section. And now it's time to develop our model very similarly to what we have done for the KNN. So let's say the decision tree, let's say, is DT. It's equal to decision tree classifier, the method that we just entered, that we just imported. And this time inside of the decision tree classifier, we don't want to input any parameter, so we go with the default. Okay, so we just built our DT. Now we use this DT to fit our data on it. Let's say DT is dt.fit, and we have, if you remember, we just split our data set into xtrain, xtest, ytrain, ytest. So again, we want to train our model with xtrain and ytrain. So let's say fitting xtrain and ytrain, just like before, and that's it. That's how we build our model, and then we can test it with let's say exactly what we have done with the KNN. Let's say this time the predicted underscore types. This time I add DT at the end, so we don't confuse this with the predicted type that we have done before for the KNN. So this is equal to DT that we just trained it with our xtrain and ytrain. And then I use the predict method, and inside of this I use xtest. As I told you, the process is exactly like what we have done for KNN, you can see the process is exactly the same and even simpler. So we haven't entered any parameters for our decision tree. So that's it. That's initially actually we made our model. So if I select all of these lines and press run, you can see that the predicted types DT is now in our variable explorer. If I open it up, you can see these are our actually predicted types, and you can see that we have the y-test, the actual values. So if you want to score this, just like what we did for KNN, a very simple way. So we just imported the accuracy score. So let's say the accuracy score and instead of, you can see that it's initially y-pred and y-true. So y-true means our actual values that are y-test, and y-pred is our predicted type. This name actually I can just copy and paste it to not have typo. So that's it. So if I just select this and press run, you can see that my accuracy is somehow like KNN. So it's about KNN with actually 6 number of neighbors. So it's about 97%. So that's a good accuracy for a decision tree. And that's it. We developed our model. The accuracy is good. It can predict the next value, that the next sample that you give to it, and it works very well. So as the next step in the next session, we are going to talk about cross-validation and actually implement the cross-validation in our decision tree model. So in this session, we want to actually make ourselves familiar with the word cross-validation, with this statement. So what does it mean? So imagine that this rectangular, this actually this box, this blue box is our data set. And if you remember, we talked about this, that if we consider, if we want to split our data set into test sets and training sets, we have done it before. So this is, for example, 20% of our data set, that is our test set, for example, and the 80% of our data set, for example, is training set. This is what we learned until now. But you may say, I don't want to just test my model with this portion, this 0.2, 20% of my data set, and test it, train it with 80% and test it with 20%. I want to make different test and training sets, and test my model, evaluate my goodness of my model. So to do that, for example, let's say I don't want just this one. I want also test this test set and the remaining as the training set. I want to also test this one and the remaining as a training set, and so on until we actually consider all of our data sets. It covers all of our data set. We actually considered all the data set as a test set, different kinds of test sets, and the remaining as a training set. So what we call this is actually k-fold cross-validation. We actually go through our data set k times, in k different times, and we separate our data sets into training and test sets with different test sets, and we test our model with that. So this is called k-fold cross-validation. So for example, if you have 200 data sets, 200 samples in your data sets, and imagine that you have 20 samples as your test set and 180 samples for the training set, but you want to do this for all of these parts. You can see, for example, this one, the next time this one is your test set, the remaining part is your training set. The third time this part, and so on until the end. if you can count this, we have 2, 4, 6, 8, and 10-fold here. So what we call this is actually 10-fold cross-validation for our 200 samples. So that was very easy and very helpful to understand that our model is not just good uh, by chance, for example, for that 200 samples. We actually tested on lots of different k-fold different samples as a test set. Okay, so we will be sure that our model is good or our model is acting bad. So let's go to the coding environment to see what we can do, how we can implement the cross-validation on the decision tree model. If I go back to the Spider, uh, so what I'm doing here is actually I want to use a method named cross-value score. I want to import it from model selection, the exact sub package that we imported train test split, you remember, in the KNN classification. So I want to use the same sub package of scalearn. So I say from scalearn dot again model selection, and I want to import. This time I want to import cross underscore. You can see the different suggestion for you. I want to use cross val score. So I'll use this one. So that's it. I just select this and press run. Now I have imported the method cross val score from model selection sub package. And now I want to use it. And there is no need to use xtrain and xtest this time because I want to use the x and y that I have actually created in a pre-processing stage. If you remember, this is our x and this is our y. And if you want to check this, you can just open it up in the variable explorer. So this is our x and y. So I want to use this 150 data here and 150 labels actually here. So I want to use this. I don't want to use xtrain and ytrain and xtest and ytest. So let's say our scores, I want to put my scores into a variable named scores underscore dt. I want to implement this cross-validation on my decision tree. So I use the cross-val score that I just imported. So let's just copy and paste it here. And inside of the parentheses, there are several parameters that you should define. The first thing that you should define is actually the model. So we have previously developed our model. As you can see, our decision tree has been developed before. So it's DT. So our model is named DT. Okay. The next step is defining your data sets. So I should say X and Y. X is my features and Y includes my targets or labels. And then the last thing that I should define is the number of folds. That's so easy. So I should say CV is equal to 10, for example. I want to have 10-fold cross-validation. So that's very easy and straightforward. I just mentioned the name of my model, that is decision tree that I have developed it previously, and the x and y as my features and my label, and the CV that shows the number of folds that you can have. So I explained it in the presentation section. What does it mean k-fold? So this is the k number actually. So if I just select this and run this again, you can see that a new variable created here named scores underscore dt that we just made. So if I open this up, you can see that I have set of numbers. I have 10 numbers here. As I asked the cross-value score, I want 10-fold, so it gives me 10 scores for different set of test sets. So I have 10 numbers, for example, for this test set, the accuracy is actually 100%. For this test set is about 93%. For example, for test set number 6, it's about 86%, is not very good. and for example, number 7 is about 93%, and so on. So now you can, for example, get an average from these uh, accuracies and give the average of the accuracy, report the average of your accuracy as the results of the accuracy of your model, and that will give a better understanding from your model and how your model is acting.
Watching.
We are actually starting our new chapter, chapter 6. We finished the classification, and now we are going after another interesting and important model, supervised learning models, actually, that we call them actually regression. So if we start again, I want to review some of our learning methods that we learned together. So we said that the supervised learning actually is classified, is categorized into two important categories. The first one is classification, that is mainly for discrete data. And we talked about this, and we said, for example, we can have a binary class or multi-class, and at the moment the what is the binary class that we are talking about, the two classes 0 and 1, true or false, or the multi-class that we have several classes, not just two, just like what we had for iris data set. Here we had also two examples that cover both of these. Multi-class is like the iris data set that we actually covered it in lots of our classification models, and also the binary class, just like the breast cancer data sets that we went through, that it was just 1 or 0, that means cancer or not cancer. So you remember that we did this for breast cancer. We actually developed a model, classification model, to find that the patient has cancer or not. And also for the multi-class, it could be an application for diagnosis based on symptoms. Also, the other method of supervised learning that we are going to learn in this chapter is regression. So, on the other hand, that you remember the classification was for discrete data. This time we are dealing with continuous data. So imagine that you have been asked by the real estate company to develop a model for them in order to, for example, predict the price of the house. Okay, so to predict the house price based on different feature, you need to use regression because you're dealing with some continuous data, and it's not discrete anymore. And we need to predict the next data that include in this continuous data. So we need to use regression, and we are going to know in this chapter we are going to understand the concept behind regression and how to develop the model related to regression. So as the first model of the supervised learning regression, we're going after understanding multiple linear regression, so or MLR. So let's first understand the concept behind the multiple or multi-linear regression, and then we're going after developing the model. So imagine that we have x and y, x in vertical, horizontal, and y in vertical. So x is actually our independent variable. Now I imagine that you understand the difference between independent and dependent variable. So x is our independent variable, and y, as you imagine, is our target or our label or our dependence variable. So and just imagine that we have a 2D we are dealing with a 2D problem that we just have one independent variable, one feature we have, okay? One feature and one goal. And imagine that this label, this goal, this target is actually increasing with increasing the x, something like this. So these are our examples, actually. These are our samples. So in order to find a model for this with a multiple linear regression, first, forget about multiple one. First, imagine that you want to do a linear regression. You want to actually find a model by just fitting a line, a simple line here, okay? So let's say this is our line, and this is, imagine that this is the best fitted line in our data. So you cannot find better than this line. So the formula for this line is somehow y is equal to a1 as a constant of x and plus a0, okay? Imagine that this is our line. So actually this is our model. So this is what we call simple regression, okay? So until now, we understood how to develop a simple regression with our 2D model, that we have just one independent variable and we have a target, and we just fitted the best line here, and that will be our simple regression. And as an example, just imagine that for the house, this is the number of the number of bedrooms, for example, just an example. And this is the price of the home, okay? Number of bedrooms in the house and the price of the house. And let's say, for example, this is the line. The line is y is equal to 2x plus 6. I know this is not this line, but imagine that this is the imaginary line. And if the number of bedrooms is equal to 4, so the prediction of the price will be very easily by saying, okay, this x is 4, so to predict that, the price will be 2 times 4, that is 8, plus 6, that will be 14. Okay, so prediction with simple regression is like this. We just find the best fitted line in our data with a simple regression, and we have just one independent variable here, and just by putting the new independent variable into our model, into our line, it can predict actually the y as our price, as our label for us. Okay, the price is 14. So let's say okay, so what is multiple linear regression? So usually we are not dealing with just one independence variable. We are not just dealing with number of bedrooms. We are dealing with several independent variables. So for example, imagine that we have another x, that is another independent variables, that is x2, and it's year of construction. So the year of construction is another important feature in defining the price, in specifying the price of the home. So to add this in our simple regression, it's not any more simple after this. It will be y is equal to a1 x1 plus a2 x2, the new one, and plus a0. And imagine even we have another one, we have location. The location is another important feature, another important independence variable that we have here, that we want to add to our model. So the model will be like this time. We have 3 independent variable and 1 target. So you can see that I cannot visualize this because we are going more than 4D after this. But just imagine in your mind as a 3D or 4D. It's just but we cannot visualize it here in our computer. And then we have also the last one, that is, for example, xn. Okay, you can have n number of independent variable here, x1, x2, x3 until xn, and the model will be something like this. The line will be something like this, that y is equal to a1 x1, a2 x2, a3 x3, and so on until an xn plus a0. So that's a n-dimensional line, something like that, okay, that we cannot see it here. We cannot visualize it actually, but we can have the formula. So this is called multiple or multi-linear regression, And that is simple regression. So now I think you understand the difference between multiple linear regression and also the simple regression. And yeah, that will be actually our model. And to in order to develop our first regression model, we go to the Spider environment in order to first pre-process our data. So let's go to our coding environment. As you can see here, I just made a new editor for myself here, named regression. Just save it, and we want to start with importing the data. So we want to work this time with an interesting real estate price data set in Boston. So let's first import the data sets, just like what we did for iris and breast cancer data sets. So to do that, I'm saying from scikit-learn dot data sets, yeah, import. Okay, if I just say load, I will have several options for as a suggestion. You can see that this is the breast cancer that we worked with. This is the iris data set. The first one is the load Boston. So if I just click on this, that's it. With just selecting this and running it, I can import the load Boston. But before doing that, I want to import some of my important libraries that maybe I will work with them during the developing these models. So let's say I want to import again NumPy as MP. I want to import pandas as PD, and I want to also import, maybe I want to visualize something, I want to import Matplotlib dot pyplot as PLT. Okay, so now I want to just select these 4 lines of code and import my library just by pressing run, and that's it. Now I have my libraries imported, and also the data set that you wanted. I want you to pause the video right now and try for yourself, just like what we did for iris and breast cancer data sets. Just put the Boston data set into a variable, copy it into a variable, and also make x and y. I mean, x is our independent variables, data, and also y is our target. Just put this, call these data from the load Boston, the variable that you just created, and create an x and y. If you remember, just go further ahead and also create x train and y train, x test and y test by splitting the data sets into, for example, 25% as a test size, 75% as the train size. And then come back to video. We are going to do this with together. I strongly suggest to do that as an exercise so you can remember what we have done in the pre-processing stage of the classification. So now we want to do it with together. So let's say our Boston. Let's say my variable is named Boston P. Okay, Boston price, because it's about the price of the house. Different houses in Boston. So let's say I want to use load Boston and the empty parentheses. And if I just select this and press run and go to the variable explorer, you can see that I have actually copied the load Boston library, load Boston dataset into the Boston underscore P variable. So if I just open this up and check the metadata, the information of the dataset, you can have lots of information about the different features of this dataset here, and from when to when it gathered, the number of instances, and lots of other things. For example, you can see that number of instances is 506. We have 506 samples. And number of attributes, number of our features or our independent variables are 13 numeric and categorical predictive variables. So that's it. We can close this, and these are our data. These are our 13 actually data from 0 to 12. These are our features or attributes. And like close and go to the features, go to the target. So this is our target. This is actually our price. You can see that we have 506, just like our features here, target, the prices. So it means that let's evaluate it together. This is our data, okay? Different feature names. We will talk about them. For example, number of bedrooms, blah blah blah, something like that. We have 13 of these, okay? And each sample, for example, this sample with this data, at the end, the price is 24 million, or we don't care about the units, okay? And the second row, the same thing, the price is 21. The third row, the price is 34. So you can see we have number of data, number of features, and then dependent variable or target here as our label, okay, as our y actually. So this is my y, these are my x1, x2, x3 until xn, if you remember from the presentation. So that's it for the, and you can see the feature names here as well. These are our feature names, 13 feature that we had, and also the target that we discussed. Okay, now that you're familiar with the Boston data set, you are very welcome to go ahead and pause the video and search more about this data set as much as you like. Now we can go to the next stage, that is creating our X and Y. So let's put our data in the targets and targets into X and Y. So let's say our X is equal to, I want to call the data, okay? So let's say Boston underscore P that we just created. And I want to say inside, I want to say dot data. I want actually this data, this to be copied in X for me. And my Y is, as you guess, is my label, my target actually. So I want to say Boston P, oops, dot, this time I want to targets. Okay, so I want data to be here copied. Actually, I'm calling the data from the Boston data set to be copied in X. And I I'm calling the target here as my prices to be copied in Y. And if I just select these two and press run, you can see my X and Y are created very easily. And that's it. The next step now, we want to actually split our data set into training and test set as we learned before. And I imagine that it's very, very easy for you now. First, let's import the train test split method from the model selection of the scalearn. So let's say from scalearn dot model selection, I want to import train test split. Okay. And now I wanna, if you remember, the order was very important. So the first thing is my X train. The second is my X test. Sorry. The third one is my Y train. And the fourth one is Y test. Again, the namings are not important. The order is important. This is equal to train. I'm using the method train test split that I just imported, train test split, and inside of the parentheses, I'm saying first my X and then my Y, and it goes to split it for X train and X test and Y to Y train and Y test. And I want my test size to be equal to 25%, something like that, 25. And for sure, my train size, you don't have to specify it, but here I specify it for you. So it's 75%. And also, I want to say the random state, if you remember, was very important because we maybe come back and compare the results with other models. So let's say the random state is equal to 76, any number that you like, just as a code, private code for this train test split. Okay, so that's it. If I just select this line and press run, oops. Okay, first, sorry. First, you need to import this line. So let's say, okay, now the train test split imported. So first, select this line and run, and now select the second line and run again, and now it works. So now I have my X train, X test. As you can see, my X train is this. The size is 379, and my X test, the size is 127. So it's like 25%, 75%. And my Y test, exactly like the X train and test, it's 127 and 379 as Y test and Y train. So yeah, you did it. But before we go into the developing our first regression model, actually our data need to be normalized. If you remember the normalization in the pre-processing chapter, we talked about we have several. You can see that our data, our features we have 13 features. Okay, some of them, for example, this one is 0.693, but this one is 4.5. But the computer does not understand, the machine does not understand that this one is as important, equally important to this feature. So we need to normalize them. We need to make them in same range so that computer understand that these are all in same range. Okay, so we need to have a unique range for that. But just remember, we have not we have, this is not a must for for multiple linear regression, but we are doing this because we need it for other models than multiple linear regression. But why don't we need this for multiple linear regression? Because we have different constants for each feature. We have A1, if you remember, for X1, we have A2 for X2, A3 for X3, and also A13 for X13, okay? So because we have different constant, we don't need to normalize our data, but we are doing this. This is if you normalize your data, it doesn't have negative impact of your result of the model, okay? But we are doing this because we need this for other models. We need this for other models than the multiple linear regression, the MLR. So let's do this. Let's do this as our pre-processing stage. As you guess, I want to import from scale-learn dot pre-processing. I want to import. I want to use min-max scalar. I want to use min-max scalar, and let's say if you remember the min-max scalar from pre-processing, I want to, for example, put it in a variable name sc. Scale is equal to I want to use this method that I just imported, so min-max scalar, and inside of the parentheses I want to mention the range of my feature, so feature range, feature underscore range is equal to, let's say, 0 and 1. Okay, sorry, 0 and 1. So I want to bring all my features between 0 and 1 as the same unique feature range. And let's actually fit the variable that we just made in our data. So let's say xtrain is equal to sc that we just created that fits I use fit underscore transform. And inside of the fit transform, you need to actually specify the data that you want to transform. Here our data is, for example, xtrain. Okay, and exact same thing for xtest. So I just copy it and paste it here, and I just change the xtrain to x underscore test. And here as well, the train, I should change it to test. Okay. We also need to do this for the y train as well. We don't need to do this for y test because at the end we want to compare it with the y test, compare our prediction. So you don't need to actually normalize the y test. Just y train is here. Y train is equal to sc dot fit transform again. And inside of this, I want to use y underscore train. Okay. And if I select these two, and if I select all these lines except this one, I will tell you why. If I select these ones and press enter, press run, okay, we have a problem here. I think I have a, okay, that's it. I have a typo again. So this is feature. Okay, that's now right. Now if I select these 4 lines again, sorry for the typo, and press run, you can see that my xtrain and xtest, if I open them again, now you can see that all the features are in the same range. All of them are between 0 and 1 here, and also here, all between 0 and 1. Okay. Just like what we explained in the pre-processing stage, pre-processing chapter. But why I didn't select the Y train? Because if I select this and press run, you can see that I will get an error here. I will get an error that's saying I expected 2D array, but gotten 1D array. And that's because actually here, the dimension of this Y train is different from the X train and X test, and you need to reshape the Y train before doing this. So to do that, it actually Python is giving you a hint. If you read this, it's saying that reshape your data either using the array reshape -1 and 1. So let's do that. Let's say I want to reshape my Y train and say Y train before that line. I say Y train is equal to Y train dot reshape, and inside of the parentheses, exactly like just like what Python is suggesting, we want to have -1 and 1. So if I do this before running this line of code, if I select this and press run, now my Y train is reshaped. Now if I select this and press run, you can see that it successfully actually transform my Y train into between 0 and 1. So if I open up the Y train, you can see that all the data now is between 0 and 1. Okay, now we finished we actually finished the normalization part, and we actually finished the pre-processing part, and we are ready to develop our first regression model, and that will be very, very interesting to see how your model can predict the next price of the house. And that will be in our next session. So are you ready to build your first regression model or not? In the previous session, we actually built and made our data ready in order to develop our model with. We have our X train, we have our X test, and Y train and Y test. So let's start. Actually, the process is not very different from what we have done in a classification. So you're familiar with the process. Uh, to do that, just keep in mind that as we mentioned, the differences between the multiple linear regression and simple linear regression uh, in the presentation. We use linear regression, simple linear regression, when we have just one feature, and we use the multiple linear regression when we have several features. So the good thing is there are no separate package for these two. And for both of them, we use linear regression method from linear model package, subpackage of the sklearn. So let's import that as our first line of code. Let's say from sklearn. So this time I want to use the linear model subpackage. So let's say linear underscore model. Yeah, this suggestion. I want to import from this subpackage the linear regression method. So linear regression. Yeah, this one. So we imported the actually by selecting this line and pressing run button, you can see that now we imported our linear regression method from the linear model subpackage of the sklearn library. Just like what we did for the classification, now we say the linear, this is the variable name, for example, linear R, okay, linear regression is equal linear regressor. This is our variable name is equal to linear. I want to use the same method here, so linear regression, and that's it. I don't want to put something in parentheses. Let's go with default. And the next line is let's fit our data to this variable. So let's say linear R that we just made dot fit, and inside of the parentheses, as you guess, I should mention xtrain and ytrain. So I say xtrain and ytrain. And now our model is ready to predict, and I have my test set to test it. So very easily, I come here. So first, let's actually select these three lines of code and press run again. Now our linear regression model is ready to predict. So let's say I want to put my predicted values into. I want to create a variable named predicted underscore values, for example, and another one. Let's say this is R. Okay, regression or MLR. Okay, so this is equal to linear regression, the model that we just feed our data on it, dot predict method, just like previous times that we did it for classification. And inside of the predict, we use, as you guess, xtest. Okay, so we are saying actually use this linear regression that we just feed our data on it, xtrain and ytrain. We actually trained it with our training sets and use it to predict the X test for me. If I give you the X test, what will be my price? What will be my Y test? I have actually my Y test here, but I want to see what model predicts so I can compare it with this. So if I do this and I just select this line and press the run button, you can see that my predicted values are here, but the problem is these are not the predicted value, actual predicted values. These are normalized predicted values because we used we actually scaled them between 0 and 1. So to bring them back actually into the actual values, we need to transform them by the method name inverse transform. So to do that, I say, let's copy and paste this name here. I want to say bring this back for me. So I say use the SC. You remember the SC we just made a variable of a min max scalar, feature range 0, 1, and we put it in SC. We used fit underscore transform in order to actually scale our data between 0 and 1. Now I want to use another method, not fit transform. This time, the other method is inverse transform. Okay, just this suggestion. I want to use not fit transform. This time I want to inverse transform. Actually, I want to inverse my predicted values into the actual format. So I just copy and paste this here in the parentheses. So I'm saying that actually inverse the normalize the scaled the predicted values and copy it into the predicted value underscore MLR again. Okay, so if I just select this and press run and then check my predicted values, you can see now we have our values, our actually prices. Okay, and if I just open up the y-test, these are our actual values. That's actually this is the real actual values that we have for x-test. These are the prices, but these are the predicted values that our model actually predicted. Now, by look, we can see that the model is not acting very bad, but it's not acting very good. But how should I evaluate my model? I have my predicted values. I have my real values. I want to compare these numbers, these values one by one with together. But how should I do that? In the next section, I'm going to explain how you can evaluate the regression models, and it will be very interesting. So after that, you will be able to evaluate your models very easily. Yeah, that's it. Let's go to the next session to find out the concept behind the evaluation metrics. So, as we discussed in the intuition session, we have several metrics, evaluation metrics, to evaluate our linear regression that we just imported, that we just created in the previous sessions. So to do that, I want to use some of the libraries and importing them from scikit-learn. So let's say from scikit-learn metrics. So I want to use the metrics subpackage, and it can give me lots of opportunity to use several evaluation metrics. So first, I want to import mean square error, mean. You can see that we have several evaluation metrics here. I told you there are dozens of evaluation metrics out there, but I just explained some of the important ones for you. So the mean absolute error as the first, mean squared error or mean absolute error. Let's start with mean absolute error, and then I want to import from, just like before, scikit-learn that metrics. I want to import, this time I want to import mean absolute error I just imported, mean squared error this time I want to import, and I also want to import from scikit-learn.metrics I want to import R2 underscore score. Okay, this one. So this is our mean absolute error, mean squared error, and R squared that we talked about. And also to calculate the root mean square error that we discussed, I need to import math library. So very easily I say import math as well. And to just select these 4 lines and press run. Now we imported our related libraries. Let's say start with the mean absolute error. To calculate that, I create a variable so I can see it in my variable explorer. Let's say this is MAE, mean absolute error, is equal to just using the method that I just imported. So let's say mean underscore absolute error, and inside of the parentheses, uh, let's check the help so we can find out what are exactly the things that we should enter. As you can see here, for the parameters, the important ones that you should enter is the y true, that is your actual or observed values, and y pred, that is your prediction values. Okay, we just keep the others as the default, and let's go back to our coding environment and say, so the first one was the actual value. So my actual value is this y test, if you remember, that we just split it from our test set. And let's say y underscore test is my actual values. And my predicted values, if you remember, I just put them in a predicted values MLR, if you remember. So this one was, you can just copy and paste it here. Is your predicted values, and that's it. I want just these two parameters. And if I just select this and press run, you can see that MAE is here. It's 2.9. Okay, so as you can see, you know the range. If you developed your model, so you know the range. If I just open up my y test, you can see that the range is somehow, by just looking at it, is somehow between 8 to 30, something like that. So the range is like that, and the error that you receive by your prediction is 2.9, is about 3. Okay, so your model is not acting bad, but it's not perfect. So yeah, this is our first evaluation metrics. But for somebody that doesn't know your range and doesn't know your data in a detail, this number could not make any sense. So he cannot, or he or she cannot uh, say that, okay, your model is good or bad, okay, with this 2.9. But for you, as you know the range, you can see that this is not a bad number. So the next one is the actually mean squared error. And to do that, so let's say I want to use mean square error is equal to, I want to use this time the other method that I imported, mean squared error. And as you can see here, the suggestion here is y true or y pred. My y true or y, the actual values, or y test again, and my y pred, you can just copy and paste it from here that we just entered. So if I just select this line and press run, you can see that my MSE, or mean squared error, is about 17. Okay, this is a very big number because it's a squared error. So to get a better number from this, we need to have a root of it, that we call it root mean square error, that give us better sense from our error. So I just use the math library that I just imported, and I use the actually math dot, I use the sqrt method. So I say sqrt, this one, and inside of this I want to have the sqrt of the mean square error that I just calculated. So you should just copy the this one here, msq. So I want to have the sqrt of the MSE, that is my mean square error, and put it in RMSE for me, that is my root mean square error. So if I just select this and run, you can see now with this root mean square error, I have better sense, that is 4.1. And again, this needs you to know the range of your data, this 4.1. And if somebody doesn't know the range of your data, this does not make sense that your model is good or bad. But with knowing the range, This for 4.5, 4.1 shows that your model is an average model. It's not perfect. It's not very bad. And let's go to more interesting ones, the R square. The R square actually is the same as the previous ones, the calculation of it, because we actually imported the related method. So I just want to say the R2 is equal to, I want to use the method that I just imported. So I should say R2 underscore score, this one. And inside of the parentheses, again, I should mention the y-test, that is my actual value, and the predicted values. So just copy and paste them here. And if I select this one and run it, you can see that R square here, this one, in my variable explorer is about 6.9, is 0.69. So it's about 60%, let's say it in percent, for example. So 0.619 is about 0.7, is not a bad fit. So it means that we actually have a good fit, but not perfect. 0.7 is not very good, but it's better than average, okay? So this is the R square. Even without knowing the range of your data with this R square, that is 0.7, anybody can understand how your model is acting. And at the end, the last but not least is the mean absolute percentage error. That is, I like it very much. And I want to show you how to calculate these evaluation metrics without using libraries, because it's not very difficult. You don't have to use libraries. You don't have to use the methods of the scale-learn to calculate these. You can just calculate these yourself in Python. So it's not very difficult. So as an example, let's calculate this one, the mean absolute percentage error, that I like it so much, and it can give you so much sense about how your model is acting. And to do that, I want to define a function here. So let's say I want to define mean absolute underscore percentage. I hope I don't have typos. Underscore error, something like that. This is the name of my function. And inside the function, I want to have y true, just like these libraries, y true and y pred. Okay. So don't forget to put the colon here and go to the next line. And here I want to say, I want to put something here to make sure that my ypred and ytrue is numpy array. If they are not, they are here in this example of our code. But in case it's not, and I want to use this 3 line of code, for example, for another model that the ytrue and ypred are not in the numpy format. So this line will change the, for example, data frame to numpy format, something like that. So I want to say the y underscore true and y underscore pred is equal to np dot array, and okay, inside of this is y true again, and put a comma here and say np that's array again, and let's say y pred. Okay, and we already imported the numpy here at the start of our code. As we mentioned, we may need them. So I want to use this line in case our y true or y pred is not an array, so it can change it to array format for us. And let's say, let's go to the next line as, and I want to return actually, now I want to put my formula here. So what is the formula? So return np that's mean, the average, And inside of the parentheses, I want to mention np, again, use the numpy.abs, that means the absolute of the y true minus y pred. And if you remember, the formula was this, the absolute of y true minus y pred, and the summation of that actually. And I should actually divide this number by y true again. I hope you remember the formula. If you don't, just pause the video and go to the previous session that we talked about the formula and how to calculate the mean absolute percentage error. I'm just writing the formula here. It's not very difficult. It's not very complicated. Just this is the formula, and I'm using the NumPy package to just create this formula. This is the average of the ABS, that is absolute of the y true minus y pred, divided by y true, and I think that's it. And at the end, we need to just multiply this by 100. Okay, so I think if you don't have problem with the parentheses or stuff, we shouldn't get an error here. So if I just select this line in order to define my the function that we just created and press run, you can see that now my mean absolute percentage error function is created, and now I can use this for any model that I like. I just need to put the y true and y pred, and it will calculate the mean absolute percentage error for me based on this formula that I gave it to it. So let's do this. Let's make a variable name mean absolute percentage error, and let's use this function that we just created. Let's just copy and paste it here. And let's say inside of the parentheses, I want to have my y test as y true, and I want to have y pred. The y pred here is this one. Okay, let's say this is my y pred, just like what we did for the previous ones. This time I made this function myself. The previous time I used the libraries, and then inside of parentheses I used the y-test and predicted values. This time I made the function myself by just putting the formula here, and that's not difficult. You can do the same as an exercise for MAE or MSE very easily, just like this. And I strongly suggest to do that. That will be very interesting after you wrote this line of code. And now I'm using this function in order to calculate the mean absolute percentage error for y-test and predicted values and put it in MAP. So if I just select this line and press run, you can see that the MAP is now here, the mean absolute percentage error, and it shows that we have 43% error. So that's now giving us a very good sense without knowing the range of our data. That our model has 43% error. So that shows lots of error. So the error is not very high, but it's not good as well. So let's see if we can just improve this model, improve this prediction, and make our error less and our accuracy higher in future sessions by developing other models. Let's see how it goes. That's it for this session. Until next session, take care and enjoy using data science. So in this session, we want to go after another important learning model that we call learning algorithm, actually, that we call it random forest regression. But what is random forest regression? To start, I want to first talk about an important learning method that we call it ensemble learning. So in ensemble learning, we actually use several several learning algorithms, similar algorithms. Like, for example, imagine that we use K and N decision tree in Evbase with together, and the decision will be made based on the results of all these three algorithms. So we use all of these actually algorithms in order to have a robust model. Or there's another option that we can have one algorithm and use it several times. So we can use several algorithms together, or we can use one algorithm and use it several times. So we have several, the combination of these several models will create our ensemble learning model. So all the things that we are doing here is actually to create a robust model. And in this session of the regression tutorial, we're going after random forest that is actually one of the ensemble learning types. And the type is actually like this, that we use several decision trees with together, as the name is clear, random forest. So we are using several decision trees. It's actually a combination of several decision trees that we use that creates our random forest model. But to make it more clear, imagine that we have 1, 2, 3, 4, about 9 trees or more than that, okay? And we want to make a random forest with these trees, with a combination of these trees. Remember, we used these trees and we made them upside down in order to make our decision trees, root node, branches, and also the decision nodes or chances that we had as the middle nodes. So imagine all these decision tree, the combination of those will create, and with actually the use of the prediction results of each tree. Each tree is important in our results, and with the prediction results of all trees together, we make our final decision. And this decision is actually the decision of our random forest model. And you can use the random forest for, if our data is continuous data, we can use it for regression. If it is discrete data, we can use it for classification. But in this session, actually, we are using the random forest for as a regression method. And the last thing is some of the important parameters. Let's take a look at them because we need these parameters in developing our models. So I want you to be familiar with these terms. The first one that is very important is the n underscore estimator that actually shows the number of trees, number of decision trees that creates your random forest model. So as I explained in previous slide, each random forest model actually includes several decision trees that create the final decision, and the number of these decision trees is actually n underscore estimator. So if you see this term in our development section, this term means the number of trees. So imagine that you have 100, you're using 100 trees to create your random forest model. So this means that the n underscore estimator is equal to 100. Another important parameter is, imagine that this is your random forest algorithm. And if you remember, it's a little bit similar to what we have done for the decision tree, and I explained it there. Roots that it starts from the root node, and you have some chance nodes here in the middle nodes, and at the end you have decision nodes, and also the branches. And but here in the random forest, for example, we don't want to continue until the end of the decisions, and sometimes we want to stop this branches from and we don't want to go until the end. So for example, imagine that we want to stop it here because of several reasons. For example, sometimes you want to decrease the computational time. Sometimes you want to prevent the overfitting, and don't worry about the term overfitting. I will explain it completely in the last chapter. But just remember that we are doing this because of the reason that we stop the branches, the creating the new nodes, and we say that okay, this is our last nodes, and we will make our decision based on these nodes. So uh, by creating this line and stopping it here, we are actually making another term that is called maximum depth. So this is the maximum depth of our random forest, and the number of trees are called n underscore estimator. So just remember these two parameters when we go to the when we go and for developing our model. This will be helpful, and it could help you to understand more what are these parameters. So that's it for today's session. In the next session, we are going to develop the random forest model in the Python environment. And until then, keep exercising and enjoy using data science. So in this session, we are going to develop our random forest model that we discussed it in previous session in intuition. It's very easy. So just we can do it together. And let's start by just because I removed and cleared my console. And this time I want to just go to the start of my code, the pre-processing section that we code with together before MLR, and just select all of these lines for the pre-processing and press run. So now if I go to my variable explorer, you can see that all the variables that I made, for example, xtest, xtrain, ytest, ytrain, they're all there and I can use them. So just we can come back here in our new area, and now I want to first import my package. And the package here, as we discussed it in the intuition part, the RF is a class of ensemble learnings. And now we need to import it from this class, actually, this class of sklearn. So let's say from sklearn dot ensemble here in the suggestion, I want to import random forest regressor. So let's say random forest. You can see that we have random forest classifier and random forest regressor. So we want to have a regression, so we go for random forest regressor. And just select this line and press run. Okay, now our package is imported. And now we can use the method random forest regressor that we imported it from ensemble subpackage of the sklearn library. So now the procedure is exactly like before, like linear regression. So as an exercise, just pause the video. You can pause the video and go ahead and just write the related code. It's just 2 or 3 lines of code, and then come back to video. Then we can do it with together. So let's say, just like before, I want to make a variable named random underscore f. Okay. And I want to use this method that I just imported. I can just copy it and paste it here. And inside of the parentheses, I want to just mention the random state is equal to, for example, 33, any number. So you may ask yourself that in the previous presentation, I talked about several parameters. So why should I go just with random states and nothing here? The reason is I want to show you if we go with the default values for the parameters, what are the results, and then if we come back and set the parameters, what will change in our results. So let's see that. That will be a very interesting process. Just for now, let's put just the random state as a fixed number so we can get the same results when we come back. And let's continue our coding, which is feeding our data, our training data into our model. I'll just say the random underscore f that I just created. As you guessed, that fits. And inside of the parentheses, I should just mention X train and Y train. And yeah, that's it. After this, we fit our model. So let's select these 2 line of code and press run. Now we can see that our random forest regressor model is actually created and ready to predict. Now I want to start my prediction by using my X test, just like before. So let's say the predicted underscore val underscore random forest, something like this, is equal to the random of the model, and I want to use the method predict, and inside of the parentheses, I want to use X test. So I'm giving the X test to my model in order to predict the Y test for me, but I actually have the Y test here, and I want to compare the results of my random forest model, the prediction, with the actual value that I have here, and calculate how much my model is good. So to do that, we just should select this line of code and then press run, and now you can see that our predicted val RF is here. But again, this is not what we want. If you compare it to Y test, this is the actual value, and this is, as you guess, these are the normalized data, just as I discussed it in previous sessions. So we need to do the same thing here, what we have done for the MLR here as well, in order to make actually revert our normalized data to scale data to the actual data that we had. So to do that, first we need to, in order to inverse and transfer our predicted values, again, we need to first reshape our predicted values. So let's say my predicted value RF is equal to predicted value RF again. So let me just copy and paste this here. And I use the reshape method. And inside of the parentheses, I use -1 and 1. And if I select this and do this, now I reshaped it. Now I want to use the inverse method. Actually, very easily, I say the predicted val or f, my predicted values are equal to, I want to inverse it. So if you remember, we have done the same thing for the MLR. So let's say SC, that was, let's go back so I can show you. So if you remember, in the pre-processing stage, this was the SC that actually we created. And this is our feature scaling that is between 0 and 1. In that time, we actually feeded our data using feed transfer method. This time, we want to actually inverse it. So we use sc dot inverse transform. You see, the suggestion is here, sc dot inverse underscore transform. And inside of the parentheses, you should just mention the name of the variable that you want to change, and that's our predicted value. Okay, so if I just select this line of code and press run again and check the predicted value again in my variable explorer, you see now we have inversed our values successfully from normalized to actual values. And now we can compare this with our Y test, our observed values. These are predicted values, these are observed values. And now we want to know how much these two have difference so we can evaluate our model. To do that, we can just copy and paste the lines from the evaluation metrics that we had for this section, evaluation metrics. I can just copy and paste them very easily from here to here. I don't want to take the time of this session. Okay, and now we can evaluate by just copy and pasting the name of this predicted val RF, just copy it and paste it here. Instead of MLR, this time we are going to evaluate the RF. So just anywhere that you can see the predicted val MLR, just copy and paste it here, 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 and here. Okay, the Y test is the same, so we don't need to change this. So we're just selecting all these line of codes and pressing run. You can see that now we have the several parameters like mean absolute error, mean absolute percentage error, mean square error, and also the R square and root mean square error. So if you forget about these parameters, these evaluation metrics, sorry, you can go back to the previous sessions that we talked about the intuition and concept of these metrics, and also you can go back to where we coded in the evaluation and evaluated actually the performance of the MLR. So just by looking at the results, you can see that just by looking at the R square, for example, you can see that with the random forest, if you remember, the R square of the MLR was about 69, 0.69. But you can see that with this R square, with a random forest model, we actually changed it to 79. So it's about 80% R square. It's about 0.8 R squared. So that means our model improved so much, 10%. So it's good. And you can see that the mean absolute percentage error is a little bit, not very much, but a little bit improved. And also you can compare other errors with the MLR. So actually, with just the default parameters that we set for our random forest, we improved the results of prediction a little bit. So that's good. That's a good progress. But but actually we use the default parameters. So what should we do now? We need to change these parameters that we call this changing parameter actually parameter tuning. What parameter tuning is just like setting a picture on a wall. You try different positions of the picture on the wall until you reach the correct position. Here we change the parameter until we get better results. At the end of at the last chapter, actually, I will put a parameter tuning session for both classification and regression. So don't worry about it. In that session, we are going deep into the how we can tune this parameter, how we can improve the parameter, how we can improve our model by changing the parameter automatically, not manually. And yeah, if you don't understand it now, don't worry about it. But I just want to play around with some parameters to just show you how it works right now and make you ready for that session. Okay, first let's, in order to do that, so for example, we want to make this better. So if I just check the, just click on this random forest regressor, I want to check the parameters inside of the parentheses by just pressing Control I and checking the help. So you can see that we have different parameters as we discussed. N underscore estimator is one of the important ones. And that means actually the number of trees that we can have. You can see that the default is 10. So if you don't define it, just like what we did, the default is 10. It means that the random forest has actually 10 number of trees. This number of trees in our model, an estimator, so means that we have n trees, so the default is actually 10. So we want to change it to another number. For example, let's say I want to change the default from 10 to 100, something like that. Let's say I want to change this, the default value. So I want to change this. I'm saying n underscore estimator. So let's do this n underscore estimator, just like what it is mentioned here, estimators. This is equal to actually, for example, 100. Let's say we want to change it to 100. And the random state is still 33 because we don't want to get different random selection. So if I just select all of these lines again this time, all of it, no different. We just changed the n estimator from 10 to 100. Now I just want to press run. And if I now check the results, you can see that the results has not changed very much. But let's say I'm changing this to this time, I'm changing this to, for example, 500. What about that? Okay, I'm seeing something here that is mentioning the change in version. This version of the Spider, the default value of n estimator will change from 10 in this version to 100 in this version. Okay, I think we are using the higher version, so the default is actually 100. That's why the results did not change. So this is the default. 100 is a default. So let's go from 100 to 10 for a starting point. Okay, so the default is 100. That was my mistake. I thought it's because here it's mentioned the default is 10. I thought it's 10, but it's not. It mentioned that for our version of the Spider, it actually of the I'm sorry of our version of the random forest regressor, it actually changed the version from changed the n number of estimator n underscore estimator from 10 to 100. So now the default is 100. It's not 10 for us, and because we are using the last version actually of the random forest regressor method. And here, if we change this 100 to 10 and just select this line of code and just press run again, and if I now check my the metrics, you can see that the R square changed from 79, 0.79 to 0.78. And it's a little bit decreased, so it means that by decreasing the number of estimator, that number of tree that shows the number of trees, actually my accuracy is a little bit decreased. So, but what about if we change it to the higher points? For example, let's say I wanted the number of estimators should be 500, something like that. Okay, so we have 500 decision trees in our model. So now let's select this line of codes and press run. Now you can see that it actually improves. Our R square is going to 0.8. It was 0.79. When we change it to 10, it went to 0.78. And when we change it to 500, it goes to 0.8. So it's not a very big improvement, but it has some improvement. It's small, but it is there. And also you can see that the error is actually decreased for 1%. It was 42%, now is 43%. So by increasing the number of estimator, I actually increased the accuracy of my model and decreased the error a little bit, not very much. But the thing is, with this 500 number of estimators, not 500 of the trees, we are actually increasing the computational time because your model should go through all of these trees, and we are actually, accordingly, we are actually increasing the computational cost of our problem. So you may say that, what are you saying, Navid? Because this the running of this problem, it takes actually over 1 second or 2 seconds. So what is the difference? But if you have a data set including for example, 100,000 of data instead of just 500 data, you can sense this. You can sense this computational time and computational cost. So you need supercomputers in order to solve your model in logical time, in understandable time. So uh, that's why I'm saying that you cannot increase the number of trees very much. So it should be in somehow logical level. And also the other parameters, another important parameters that we need to play with is the maximum depths that we talked about. Remember, sometimes you need to define the maximum depths to prevent overfitting and decrease the computational time, as we discussed, uh, even if your results will be worse. Don't worry about overfitting again, this term and underfitting and these terminologies, because we are going to cover this in our last chapter with the hyperparameter tuning. So my intention here was just to show you how you can a little bit tune your model. So let's just do the last change that we want here. So for example, let's say our random the other parameter that we want to discuss here, that is actually the maximum depth. Uh, let's check the maximum depth defaults. I forgot it, so let's say, okay, the maximum depth here, the default is none. It actually doesn't set a maximum depth for you, but here imagine that I'm setting a maximum underscore, sorry, max underscore depth. Max underscore depth is equal to, for example, let's say 20. Okay, so if I create this maximum depth, I actually stop my model to go until the end of the branches. It is stopped somewhere. It stops at the number that I define. So if I just select these lines again and just press run, and now if I check the results, you can see that it actually, the results does not change very much. So just as an exercise, play around with this maximum depth and also the n underscore estimator. So if you can find any better results, so for example, with 13 number of maximum depths or more estimators, more trees, you can have better results in R-square or RMSE. That means that you improved your model. Just do it as an exercise, play around with these two parameters to see if you can improve the model or not. That's it for this session. So we actually developed our random forest model very beautifully, and it works great. And we actually improved the results of MLR with random forest. In the next session, we're going after understanding the concept of the support vector regression. And let's see if we can actually improve the results of the random forest this time with using SVR. That will be very interesting to see the results. So until then, take care, keep exercising, and enjoy using data science. So in this session, we're going to understand the concept of the support vector regression, or SVR as an abbreviation of it, as one of the important and famous methods in regression. And to start, let me show you this this visualization that we have went through it with together in simple regression method. So with a simple regression method, imagine that these are our datas, and if we just fit the best line here, we wanted to fit the best line to minimize these residuals. Actually, these residuals show the error. So in order to minimize these summation of these residuals, the best fitted line will be plotted. So this is how the simple regression worked, if you remember. So again, we wanted to minimize the summation of least squares of these residuals that shows the error. So the line is actually fitted in order to minimize this difference between the data and the line. So, but how the SVR acts? Actually, in the SVR, imagine that we have the same data set, and now instead of this simple line that we fitted here, this time we want to have a tube, something like this. This epsilons are called the marginal space. Actually, with defining this marginal space, we are creating something like tube. Okay, imagine this as a tube, and inside of this tube, we have several points. So some of the points that we had in our data set is actually now inside of the tube. So the points that is located inside of the tube, we don't care about their errors and how much error they have. We consider they have no errors. Okay. For now, consider the data, the samples that are inside of this tube with marginal space of epsilon. They don't have any error. But we're talking about, we want to talk about the errors of this and this point that are outside of this tube. Okay, so let's review it again. In the SVR, we are actually creating a tube with these two marginal space that we created by epsilon. And inside of the tube, the samples inside of the tube, we don't care about their errors, but the samples outside of the tube, we care about their errors. And the errors are actually called C. The upper side are called C, the downside are called C star. And actually, these C is the slack variable, is called slack variable. So what we want to do here is actually minimizing this error here by this formula. As you can see here, if we have, for example, m number of data outside of this tube, outside of this space that we defined, the summation of all these errors, all these C slack variables, will create our cost vector that I put in this red box, and the SVR acts to minimize this cost vector. So the actually fitting is actually doing by minimizing this cost vector. The SVR works to minimize this cost vector. So again, let's review it to understand it better. In the regression, in the simple regression, we fit a line. How we fit this line? We fit the best line. We fit the best line with minimum residual errors, with minimum summation of least squares residuals that we have here in order to minimize this. So for example, this is the best line with the least squares of these residuals. Okay, but in the SVR, it actually creates a tube, something like this, and put the data, put the samples inside and outside of this tube. Inside, we don't care. The outside of the tube create our cost function, create our cost vector actually that is here, and it includes the summation of the m numbers that are outside of our tube. You can see that these are our slack variables of the points that are outside of the tube. And the SVR works to minimize this cost vector. So that's it. And the other thing that I want to mention is the kernel function before we go to the coding environments again. I don't want to go to the deep into the kernel function and what is the math behind the kernel functions, but I just want you to remember that what is kernel function? The kernel function is actually used by SVR to transform the input data to the required format that it needs. So again, the kernel function, we use the SVR actually use the kernel function in order to change the formats of the data, the input data, to the required format that it needs actually. There are several kernel functions that we can use in our in developing our model. For example, just remember the names. Some of them are polynomial kernel function. We have Gaussian kernel function. We have one of the most famous one, or the Gaussian radial basis function, that the abbreviation is RBF. And we have sigmoid kernel function and also hyperbolic tangent kernel function. So these are different type famous actually kernel functions that we usually use in developing our models. So that's it for the concept behind the SVR. I hope you understand the concept now, and you are ready to start developing the support vector regression model in the Python environment. In this session, now that we understand the concept behind the support vector regression, now we want to develop our model for our previous data set that we have developed MLR and also random forest for it. Now this time we want to develop our support vector regression. To do that, I want to first import the related package from the sklearn library. To do it, I want to start importing, let's say, from sklearn .svm. So I'm using the svm subpackage. As I told you, the svm and support vector machine is actually the general term, and you can use the support vector machine for classification and also for regression, as I explained it in the intuition part. But the regression, if you use it for regression, it is called support vector regression. But the SVM is the general term, and that's why we are using the SVM, actually support vector machine subpackage of the sklearn. So from the SVM, I want to import SVR because we want to use it for regression. So that's it. Let's just import this library. You can see that we have already our previous results from the random forest here. So I just want to delete this by just clicking on this close tab button on the console. By clicking on this, you can see that it is automatically clear my console for me. So let's go back to the pre-processing stage because we don't have any variable right now. We want to import our xtrain and ytrain, xtest and ytest. So I just select all of these lines in pre-processing and press run. And now you can see I have my variables, just like what we did previously. So now I can select this line of code and run it, and now you can see that our SVR method is actually imported. Again, it's exactly like before. I want to put this on something like name it, for example, we can call it a regressor underscore SVR, any name that you like. And I want to use this SVR method. And inside of the parentheses, if you remember, we need to define a function. So if you don't remember, just press Control I here by clicking on the SVR. You can see that in a help section, you can see the parameters that you should actually define. You can see that the first parameter that you should define, and it's very important, is a kernel function. The default is RBF, so we don't want to change that, but let's just mention it here so you don't forget that we are using the RBF as our kernel function. And if you want, you can change it to any other type of kernel function that we mentioned, like sigmoid function, like tangent hyperbolic function, and linear function, and these types of functions. So let's say the kernel here is equal to inside of the quotation, I'm saying RBF. This is the way that you can define your kernel function. And by default, it's RBF, but I just mentioned it here so you know what is the procedure and how you can change it. And now if I just select this and run it, you can see that our regressor SVR is created. Now the next step, as you can guess, is the actually fitting our X train and Y train on our regressor SVR. So let's say regressor SVR that we just created, yeah, this one, that fit, and as you guess, inside of the parentheses, X underscore train that we just created in a pre-processing, and Y underscore train. So now if I just select this line and run, you can see that our SVR model is created and developed, and now you can use it for your prediction. And just with one line of code, I want to predict the X test and put it in a variable named predicted, for example, values underscore this time SVR, okay? And I'm using the predict method, so I'm using my regressor SVR that we just created, and use the predict method in order to predict. And inside of the parentheses, what should we put? Yeah, it's X underscore test. And if I just select this line and run it, you can see that our predicted value is created here. Again, just like before, these are not our values. These are normalized values. These are scaled values, actually. So we need to bring them back into their normal numbers. So we need to actually change the scale from 0 to 1 to the actual scale. So to do that, we just do the same procedure that what we did for the previous models. Let's start with I want to copy this, not type it again. So let's say, and let's go a little bit down. Okay, let's say I want to first reshape it. So let's say this is equal to this dot reshape, and inside of the parentheses, I'm using -1 and 1. And if we go to the next line, now I want to inverse my instead of fit transform, I want to use inverse transform. So let's say this is equal to, if you remember, in the pre-processing stage, this was our scale variable, so the SC. So let's use this SC. Let's say SC dot, instead of fit transform, I'm using inverse transform from the suggestions, okay? And inside of the parentheses, I'm using the value of the predicted values. And this is just copied again into the predicted value SVR, so it's just changed it. So if I select and run, okay, so I forgot to first reshape it. So now you can see that we have an error here. So first let's reshape it. Now if I select this and run it, now we can see that we successfully brought back actually our values, our scaled values, into the normal scale that they have. Yeah, that's it, and we did it. Let's take a look at them again. So this is our predicted value, and y-test is our observed or actual values. So you can see the predictions, and you can compare them by just looking at them. But let's do it precisely by using the evaluation metrics. Again, I want to copy and paste the evaluation metrics that we had, and just copy it here. And this time, as you can guess, instead of predicted value for RF, this time I want to use this predicted value. So the y-test is the same. So I just copy and paste this here, 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 and here. So you don't need to write this code several times. I'm suggesting you do it and you write the code again and again so you can memorize it and you can have an exercise. But here I don't want to take the time of the session, so I'm just copying and pasting and change the predicted values from the RF random forest, the previous model, to the SVR that we just developed. So if I just select all of these lines that I just brought here and press run. Now you can see that we have our metrics here. As you can see, the R square of the SVR model is somehow similar to the random forest. It's about 0.8. And you can see the RMSE, the root mean square, is about 3.37. And the mean absolute percentage error is about 42%, still is high. And the mean absolute error is about 2.6. So that's it. We did it. We actually developed our last model in the regression.
Watching.
So you may be surprised that I'm saying chapter 7, but it's actually chapter 4 here. That's not true. I just copied this slide from the chapter 4, but we are actually in chapter 7 and we want to start unsupervised learning. That's why I just copied this slide to review this with together. We understood the concept behind the unsupervised learning in chapter 4. And if you remember, I told you that if we had several pictures of, imagine that we have several pictures of dog and cats. And if we just give these pictures unlabeled to our machine, so the machine should be able to categorize these dogs and cats into two groups. Group 1 that are cats, group 2 that are dogs. So like on supervised learning, here we don't categorize and we don't give the label actually to our machine as an input. So let's go to start new things in this chapter. In the unsupervised learning models, let's start with our iris dataset. If you remember, we talked about the iris dataset very much in our classification chapter. And now let's imagine that we have another time we want to work on iris dataset that includes actually our features, our samples, and our labels. Okay, but this was what we worked on in the supervised learning. The difference here in unsupervised learning is this time we don't have labels. We just have features and samples, and we don't know each sample related to what flower or what species. We don't have any label for that. So that's the difference actually between supervised learning and unsupervised learning. This time we need to ask machine to label our data. Without giving it any clue, we want the machine to label it for us. The previous time we had the labels in supervised learning and we wanted to predict, for example, the next sample for us. What is the category of that new sample? But this time we have all the samples and we measured the samples ourselves and we want to give it to the machine in order to categorize it for us into 3 species, 3 labels, in order to actually label it for us. But the big question is how machine can do that and how it can just categorize our data without any clue about the labels. I want to start with a very simple example. Imagine you have several clothes and you want to categorize your clothes. You have several options to do that. For example, you can put your clothes into different, based on the different colors. For example, green in the same section, whites in the same section, something like that. Or you can do it by considering the size of your clothes. For example, the big sizes going to one section, the smaller sizes going to another section. Or another thing that is usually we are doing is actually categorizing our clothes by the season that we are wearing them. For example, in a winter, you are wearing some type of clothes, so you're actually categorizing them into winter section, summer section, and something like that. So these are all the categorization that you can do for your clothes. And the thing is, you are actually categorizing these clothes based on the similarity of them. For example, same colors going to same section, or the clothes that are good for winter going to same section. So these are all you are actually using similarity. You are actually comparing these clothes by their similarity and categorizing them by their similarity. This is actually what the computers do as well. So let's say so let's say the concept behind the what computers do for the unsupervised learning and categorizing and labeling our data is something same, and they actually use the similarities between all unlabeled samples that we are giving them in order to label our data. So and usually this similarity that we talked about, for example, for clothes, if you remember, there was, for example, color, there was seasons, but the computers usually use the distances between the unlabeled samples that we are giving them in order to find the similarities. So this is one of the distance is actually one of the metrics that they use in order to categorize our data. So now I think you understand that how machines are doing labeling for us without any clue, without giving them any, without training them by labeled one. They use similarity very easily. And this similarity is mainly distance. And next thing that I want to tell you is the clustering techniques. Actually, what we talked about until now is computers clusters or label our unlabeled data. They cluster them into different clusters, and we have different clustering technique as well. The main we have different dozens of them, but what we are actually considering in this course are three main difference. One of them is a centroid-based clustering, the other is hierarchical clustering, and the last one is a density-based clustering. These are three main techniques. These are three main clustering techniques actually that we want to go through them precisely in our course. And to start, we want to start with centroid base, and the most famous actually centroid based technique and algorithm is the k-mean algorithm, and we want to start with that. So in the next tutorial, we want to start with understanding the concept behind the k-mean as our first centroid based clustering technique. And until then, keep exercising, enjoy using data science.
Watching.
In this session, we want to actually start with k-mean clustering technique. That is one of the interesting techniques in clustering and very famous. So to start to understanding the concept behind that, first we should know that with k-means we are actually partitioning our samples into the k clusters, k category actually. By cluster, I mean if you remember the labels, those are actually our clusters. For example, for iris dataset, we had 3 labels, so we had actually 3 clusters. This is the meaning of the cluster exactly. So here in a k-mean, we want to actually partitioning our samples into the k clusters, and imagine that these are our data. These are our samples. Okay, we have different samples here, and we want to actually categorize them. We want to actually partition this data into the k cluster. The first step is actually defining the number of clusters that you think it should be. For example, k number of clusters. That's why we call this k-mean clustering. So imagine that we want, for example, this. We know that this samples are actually categorized into 2 clusters. So let's say k is equal to 2. But we don't know what each sample is, or what sample, for example, this sample is related to which of the clusters, which of these 2 clusters. So that's the reason that we use k-mean in order to understand that. So what k-mean is do that after you define your number of clusters, in the next step, it randomly select the centroid. For example, let's say in the first step, the centroid is here and here, okay? Just randomly. It may be a bad selection, but this is a random selection, okay? And it calculates the distance between these selected area in the next step to the nearest centroid. So the step 3 is actually assigning each point, each random point that has been selected to the nearest, each point to the nearest centroid that we randomly selected. So it's something like this, okay? Just this is nearest to this one, this is nearest to this one, and so on. This one nearest to this one nearest to this, and so on. And the next step, actually step 4, is updating this centroid, this time from this to, for example, this centroid, and it again goes for repeating the step 3 in order to find out the nearest samples around this centroid by just calculating the distance. And this time our clusters changed like this. And you should know that the step 5 is actually repeating the previous steps until we get the centroid does not change anymore. So for example, from now on, if our centroids are here, you can see that if I repeat the step 3 and 4 again, this centroid does not change. That means that our centroid is fixed. And now you can see that these samples are related to this cluster, and these samples are related to the other cluster that we defined that we had 2 clusters. So you may be a little bit confused still. To understand it better, I found a very, very interesting blog in the internet. And we can now go ahead and check that together to understand these 5 steps actually that I explained it for you better, better visualize it there. So if I go to the blog that I just found, you can see that this blog, you can just write this this URL here. The name is Naftali Harris. So it's a blog for visualizing k-mean clustering, and you can find some interesting stuff there. So I just opened the visualizing k-mean clustering here. And if I select, for example, I want to, it asks you how to pick the initial centroid. I want it to be randomly. And let's say our points are uniform points, actually. So these are our points. And the first step is adding centroid. As much as you add centroid is actually you're defining your k, the number of k that you have. For example, if you say 1, your k is 1. If you say 2, your k is 2. If you say 3, your k is 3. And if you say 4, your k is 4. For example, imagine that this uniform data, these uniform samples, we have 4k. The k is 4, and we define it 4, but we don't know each sample related to what cluster, okay? So by just clicking go, it goes to the third step in order to update the fourth step, sorry, in order to update the centroid. So let's say go, and you see again go, and again I update the centroid, again reassign the points, again update the centroids. You see, each time I'm saying I'm reassigning a point and updating my centroids, the centroid will change, and actually the samples that is defined in each category, in each label, in each cluster is changing. You see, for example, this one was here, and if I just update it, it goes to the blue one. So I do this until this centroid will not change. Let's do this. Okay, you see, still a little bit change, still change, still change, still is changing. You see, from now on, it's not changing. As long as I press update and resign, you see these clusters will not change. and the centroid is fixed. From the step that the centroid is fixed, from that step, you can see that the clusters will not change, the centroid will not change, and you can see that, you can say that, okay, these samples are related to the blue cluster, these samples are related to the green cluster, yellow cluster, and these samples are related to the red cluster. And that's it. That's the end of your process. That's the end of the k-mean clustering process. And let's go back to, I hope you understand it better now. Just if you want to exercise more, just come to this, go to this blog and naftaliharris.com, and you can just play around with this centroids and change the centroid and reassign the points and update it until you get your clusters fixed. And if we go back to our presentation, now you understand how these steps, these 5 steps that I just explained, worked. Again, if you want to review it, let's go back. We start from actually step 1, that is defining the K clusters, and then we randomly select centroid, and then assign each point to the nearest centroid, and then we update this centroid until in the step 5, we actually repeating this until the centroid does not change, and at the end we have our centroid fixed and we have our cluster fixed, so we know that each sample related to what cluster. So this is the 5-step main step of the k-means. And the other things that I want to explain before we go to the coding environment and develop our model is actually how k-means calculate the distance. So we talked about this in classification tutorial. So if you cannot remember these 2 main Euclidean method that we use, a line connecting 2 points, and Manhattan or taxicab geometry that actually uses horizontal and vertical lines. If you cannot remember this, just go back to the classification tutorial. I think it was in the KNN. Yes, it was in a KNN session that we discussed how Euclidean and Manhattan works in detail, and come back to the k-mean tutorial again. So these are the main 2 methods that k-mean used. For example, Euclidean method in order to find the distance. In the previous session, we talked about the concept behind the k-mean algorithm and how it works through the 5 steps that we discussed together. And in this session, we want to actually answer 2 questions. First, how we can evaluate our k-mean algorithm, just like what we did for classification and regression, and we evaluated our models. Now we want to evaluate our k-mean algorithm and how we can do that. And the second question is, if you remember, the first step of the k-mean was defining the k, and this is a parameter that you should actually give it to the machine. So how you can find the best k and what is the optimal number of k? These are the 2 questions that we are going to treat in this session together. So let's go through the first question, that how we can evaluate our k-mean algorithm and what is the evaluation metric here. So let's say these are our clusters. If you remember from the previous session that we found out, so these are the 2 best centroid that we found, and these are the 2 clusters, green and red. So imagine that the distance between, for example, this centroid and this point is something like this, and this centroid and this point is something like this. And if we have a summation of all these distances between the centroid and the samples, we have a formula something like this. So the summation of d I, for example, I1 to C1, I2 to C1, I3 to C1, and for example, n number of samples that we have here in this cluster. And here we have m number of samples, and we are adding up all the distances and in the power of 2. So the summation of all these distances in the power of 2 in these 2 clusters will give us a metric that we call it inertia. So this inertia is actually giving us how our model is acting good. And as you can guess, because we actually in the steps, if you remember, we wanted to minimize this distance. So as you can guess, smaller the inertia, the better our clustering. So this inertia should be smaller. So this is the first question that we answered. The metric that we use to evaluate our K-mean algorithm is inertia, and is actually, the formula is very, very easy, simple, super easy, and it's actually a summation of the distance between each point in the cluster in the power of 2, and actually the centroid and the points in the power of 2, and also the smaller the inertia, the better the clustering. But what about the second question that we discussed? How we actually can find the best K for our model? So we have a method named elbow method. So this method is not a standard or something fixed, but it can help us to understand the better number of K. But how it works? Imagine that you have something like this, and what is this? For example, for the K number 1, if you consider the K is 1, your inertia is something like this, okay? And if you increase your K, for example, to number 2, your inertia is something like this, and number 3 is something like this, number 4 is something like this, and so on. So you are actually testing your model with different number of Ks, and you find different number of inertia for that based on that formula that we discussed it in previous slide. And you have a graph like this, and what we understand from this graph is with k is equal to 1, the inertia is like this, but if we increase it to number of 2, you can see that the inertia will decrease dramatically. So this is important. And again, if we increase the k to, for example, 3, it's considerably decreased, the inertia considerably decrease again. Again, from 2 to 3, this happens. But what happens if we increase our k from 3 to 4? It doesn't actually decrease. You cannot sense the reduction here, and it's somehow constant after 3. So this point is our threshold and our critical point. We call this point elbow point, and actually the elbow point will give us the optimal point. So if you want to find the optimal number, it's the number that from that number, after that k, the inertia will not decrease very much, and it's somehow constant, and we don't have to increase the k anymore. So this number is actually will give you the optimal k number. Okay, that's it. Now we should do all of these things that we discussed from the previous session and this session on our coding environments, and we want to develop our first clustering model, and that will be very, very interesting. So until the next session of the clustering tutorial, keep exercising and enjoy using data science. So now that we understood the concept of the k-means, we want to start developing our first model. But before doing that, we need to have our data set. So again, we want to work on iris flower data set that you are actually familiar with from the classification tutorial. But this time we're considering not having the labels. So let's first import the iris flower dataset. You can just pause the video and do it yourself. It's very easy, just like what we did it for classification. Let's say from a sklearn library and from the subpackage of the datasets, we want to import load iris, this one. And let's say we want to have, for example, NumPy as well. Maybe we can use it. Import NumPy as MP, and also we want to have Matplotlib because we have some visualization. So let's say import Matplotlib. Oh, sorry, Matplotlib as pyplot as plt. And yeah, this is it. And let's just select these libraries and import them by pressing F9, the run button. And yeah, now all the libraries that we want are imported. The next step is just putting the iris data set into a variable so we can see it in our variable explorer. So let's say iris is equal to load iris empty parentheses, and if I select this and press run, you can see that my iris follower data set is here. Let's take a look at it. You already familiar with all the parts here, but let's go through them. So the DESCR is actually the information, the metadata, the information about your data set. As you can see, the number of samples are 150, and the number of attributes and features are 4 numeric attributes that we have. For the sepal length is one of our features, sepal width the other feature, petal length and petal width are the 4 features that we have in our dataset. And there are 3 classes: Iris setosa, Iris versicolor, Iris virginica, but we are imagining that we don't have these classes. We just have this data. Somebody give us this measured data, and we know that there are 3 flowers, for example, 3 clusters, but we don't know, for example, this sample is related to which of these clusters, which of these flowers, okay? So what we need to do is developing our clustering model to do that for us. So the only thing that we need here, because we don't need the labels, we don't have the targets actually. So this target part is actually, we're considering not having this, and we want our model to predict this for us. And we don't have the target name. So the only thing that we have is this data. So let's call this data and put it in a variable named data underscore iris, for example. And I wanna just call the data part. So let's say iris, and I wanna call the data. And put this data into the iris, data underscore iris that we have. So by selecting this and running it, you can see that data iris now is created for us. So this is the only thing that we have. We don't have anything else. And we want to ask our machine in order to categorize this into the 3 flowers that we have, and actually partition this data that we have into the 3 categories based on the similarities that they have. So yeah, let's start our developing our first clustering model k-mean algorithm in the next session. Until then, keep exercising and enjoy using data science. Welcome to this session of the clustering tutorial. So in this session, we want to actually start developing our k-mean clustering algorithm. And let's go straight to that part. First, we want to import the related libraries. So just like before, I'm using scalearn. So let's say from scalearn, this time the subpackage is actually cluster. So from scalearn.cluster, I want to import k-means. So k means. Okay, so I want to import the k-means method from the cluster subpackage of the scalearn library. So let's just select this and press run to see. Yeah, it's done, and our our method is imported. Now we need to do the same that what we have done for the classification and regression here as well, to create a variable and feed our data on that variable. So let's first create the variable name, for example, k, m, and s, something like that, the abbreviation of k-means. And it's equal to the k-means method. We're using the k-means method that we just import. And inside of the parentheses, I'm just defining the number of clusters by saying this n underscore cluster, for example, is equal to 3, because we know that we have 3 flowers, but we don't know each sample related to what flower. So let's say the n cluster is 3, and if you don't remember the parameter that you defined, you can just easily press Ctrl I and check the help again in order to find out if you forget something. So you can see that the n cluster is very important. The default is 8, so please change this and uh, do not just keep these parentheses empty. Just put the n underscore cluster, the number of clusters that you need. If you don't, it goes for the default that is 8. So that's it. That's the only parameter that we want to define here. And now it's time to fit our data. As you can guess, I'm saying KMNS that I just created that fits. And inside of the parentheses, I'm using what data that I want to fit. I have only one data, that is data iris, that I created in the previous session, if you remember, this data. This is the only thing that I have, no targets, okay? So I just give this. In the previous methods, if you remember, in the previous learnings, like the supervised learning, we actually give, in this stage, we give our model, we train our model actually with X train and Y train, but here we don't have a Y train, we don't have targets, we just have X train, we just have data. So let's say data underscore iris. This is the only thing that we have, and we want to train fit our model actually to the variable that we just made, to the model that we just made. So if I just select all these lines and press run, you can see that our k-mean clustering method is now ready to predict for us. So again, what do I want to predict? I want to predict labels. I want to predict the targets actually that we consider we don't have. So let's say our labels is equal to, I want to use my model that is KMNS. And again, I'm using the predict method. So let's say predict. And inside of the parentheses, I'm just using data iris again. Yeah. So if I just, I'm saying that using this model, that you just fit your data on it and predict the data iris. I mean, by this prediction, I mean, just give us the labels, that give us the targets and put it in a variable name labels that I just created. So if I just select this line and press run, and you can see that the label variable is here. If I just open it up, you can see that there are several labels here that created for us. 1, 0, 1, 2, 0, and 0, 1, 2, 3, a cluster that we define. And we actually have the targets, and these are the targets that are predicted for us for each sample. For 150 sample, you can see that the label size is 150. We actually have 150 targets right now. And the other thing, now we want to understand that how our model is acting good. So we need to evaluate our model. But before doing that, I want to visualize what we actually predicted with k-means. So I want to plot the scatter plots actually. And to do that, before doing that, I want to create another variable named centers, because I want to see the centers that actually defined by k-means. That will be interesting. So let's say CTN shows, for example, our centers. So this is equal to KMNS and dot cluster, cluster underscore centers, and again underscore. So with this class, actually, I'm using cluster underscore center underscore in order to find out the centers that defined by this model that I just developed, and put it in the variable name CTN. So if I just select it and press run, you can see that the CTN is created. So these are my centers that created for me for my model, and now we can actually plot the iris data set. with the targets that defined by our models, and it put it actually in the variable name labels. It's very easy. So to do that, if you remember, we cannot plot a 4D graph, so we select just two features and work on that. Just like what we did in a classification, let's plot the petal lengths versus petal widths. So to do that, I'm saying PLT dot scatter because I want to use the scatter plot. And inside of parentheses, I should define a couple of things. The first thing is X. So my X is the petal length. So I'm saying from data underscore iris, go and select for me all the rows and the feature or column number 3. That, if you remember, the column number 3 is actually, the index is 2, so 0, 1, 2. So this is 2, and the column number 4 index is 3, if you remember. This is how Python works. So here I'm saying 2, and for the next one, for the y, actually I'm saying data underscore iris, and this time I'm saying all the rows and 3. Okay, this is column number 3 and column number 4. And the last thing that I want to mention is, and it's very important, is the color of the data. The color should be actually based on my labels. Okay, so this is very important. So it actually show you how your labels work and if it's correct or not, this partitioning that your model done. So that's the first thing. The second one line is actually I want to plot the centroids that I created as well. I want to see my centroids. So let's say PLT dot scatter again. And inside of the parentheses, I'm using CTN. And inside of the brackets, I want all the rows and 2. And also CTN inside of the bracket, again, all the rows, and number 3. Why I've done this? Because this centroids is actually for all the 4 features that we have, but we just want the petal lengths and petal widths. So that's why I just did the same that I have done with the data. So I just select the column number 3 and column number 4 and extract it from my centroids. And that's it. And I want to show it because I want to specify the centroid. So let's say we have a marker here. The marker is, if you remember, we had different markers. We discussed it before. So let's say my marker is a circle. And also the color of the circle is equal to, let's say, red. So I want to see it very clearly in the visualization. And also the size is equal to, for example, 120, because I want it bigger than the other points. So that's it. And just put the labels on X and Y, PLT that X label. So this is equal to this, instead of the parentheses, you should mention it in a quotation, that is petal length in centimeter. And you can have the same thing. You just copy and paste it here for the Y label, just by clicking on this, changing this, and this is petal width. And at the end, if you remember, we just mentioning PLT that show in order to render our graph. So that's it. We actually done that. So if I just select these lines and run it, this is actually what you should have. So as you can see, our model perfectly categorizes and partitions our data into three partition. So as you can see, it is way similar to what we had actually with the real targets that we had. And these are the centroids. These big circles, red circles that I just created, these are the centroids of each cluster. So we have 3 clusters, and each sample is now we know that each sample is related to what cluster. So visually, our model is working perfect, but it's just visually. What about if we want to evaluate the inertia that we discussed? So in the next session, we are going to evaluate how our model is working, and if the k that we decided to be 3 is a good number or not, or we can change it to another number, another type, number of clusters. Welcome to this session of the clustering tutorial. In the previous session, if you remember, we actually created our k-mean algorithm model, and also we predicted the different clusters of the iris dataset and the targets actually, and we visualize it, and we find out that the result is quite good. But now we want to understand what is the inertia of this model, what is the inertia of the result of this model, and also find out that if we can make this model better by changing the k or not. So in the first step, I just want to say that it's very easy to find out the inertia. You should just say km and s, your model name, dot, and use a class of inertia. Let's say I want to say inertia underscore, and that's it. By just selecting this, if I don't have a typo, so if I just select and run, you can see that in your console the inertia is created 78. So this may not give you a sense, so you need to compare this amount with the other numbers so you can understand that if it is good or not. So to do that, I wanna make a for loop and test different number of k's and find out the inertia of our model with different number of k's. Okay, that will be very interesting. So to start that, I want to make an empty list here. So let's say k underscore inertia. This is the name that I just created. So k underscore inertia is equal to an empty list. Okay. And the next step is creating a loop, so a for loop. So let's say for I in range of 1 to 10, okay? So you want to change the k from 1, so one time k is 1, the next time k is 2, the next time k is 3, and until 10, okay? So from I in range of 1 to 10, don't forget to put the colon and go to the next line, and we just need to copy and paste the previous model that we developed here, this one. Okay, so let's say just I want to copy this line and this line. Okay, just this one. And I want to just put it here. Okay, and let's select this to make it right. Oops. Okay, now I just copy and paste these 2 lines that I just created from my model to develop my model. So I just copy and paste it here. You can see that my km and s model is equal to k-means. I'm using the k-means method, and the number of clusters are 3 here. But this time I don't want 3. I want it to be I. Why? Because I want to change it. I want to change different case here. I want to change it from 1 to 10. So, and the next thing that I want to add here is again random states, because I don't want to make some difference anytime that I want to compare. So this is again important. Random underscore states is equal to anything, any number that you like, just a code. Okay, 44. Yeah, this is this line. This line is created. And the next line is okay, we don't need to change it. We just want to fit our data set. And at the end, I want to say the k underscore inertia, the list that I just created here, k underscore inertia, that's append. And inside of parentheses, I'm just saying k mns dot. You remember how we calculated the inertia? This is the one. You can just copy and paste it from here to here. Oops, sorry, to here. To not write it again. Okay. So let's review what we have done here. I'm saying that, okay, first of all, I created a k underscore inertia list, a name that is a list, an empty list here. Then I created a loop, a for loop, and saying that, okay, for each I in range of 1 to 10, so the first time it goes for 1, it just put the 1 here and creates my model and put it in, calculate the inertia and put it in my list. The next time it goes for 2 and put the 2 here and underscore cluster is 2, and then calculates, fits the data and calculate the inertia and put it here. The third time 3 and so on until 10. Okay, so the process is very easy. It's not complicated. We are just changing the I here from 1 to 10, and we feed our data each time and calculate the inertia for that and append it to the empty list that we just created here. Okay, so it's not difficult. It's very easy and straightforward. Now, if I just select all these lines and just press run, now you can see our k inertia should be filled with 10 numbers that we wanted. So if I just open this up, you can see we have our numbers here that we wanted. So different number of inertia. Even by looking at this, you can understand that with each number of k, what is the number of inertia. But in order to understand it better, let's plot this. Very easily we can do that. Let's say I want to have a PLT, I want to have a line plot. So let's say a PLT.plot, if you remember how to draw a line plot, PLT.plot, and inside of it, I'm saying the range, my x-axis is the range between 1 to 10. Okay, just what we did here. Range from 1 to 10, I want it to be my x-axis. And the y-axis should be my k inertia that I just built here, okay? So let's say k underscore inertia, okay? And the other thing is the color, for example, let's say my color, I want it to be, this time I want it to be green. And also I want a marker so I can understand the points better. So let's say the marker is equal to circle, okay? And that's it. I just want to put a label, PLT, that's X label. That inside of the X label, I'm saying the number of K. And PLT, that's Y label. Inside of the parentheses, I'm saying number of, it's inertia. Okay, so the X is my range between 1 and 10. That is actually the number of K that we just considered. And the Y label is actually my K inertia that we created here in our for loop. And that's it. Again, the PLT that show empty parentheses. And if I just select these 4 lines and press run, you can see that it pop-ups, the graph will pop up. So it's a very good graph. We discussed it in the presentation. That's how we can find out the best number of K. So if you remember the elbow method that we discussed, so you can see that with increasing the k from 1 to 2, the inertia will decrease drastically, and from 2 to 2 to 3, it again decreased. And from 3 to 4 and 5 and 6, this reduction is not very sensible and it's somehow constant. So uh, I think the elbow method shows us the optimal number is 3, and it's true because we in a real case study we have 3 types of flowers, and we know that. So from the if your problem does not specify the number of k and you don't know exactly what is the number of k, just go randomly, start randomly with a number, and then you can use this for loop in order to find your best number of k based on inertia and the actually as an evaluation metrics, and also the elbow method that we discussed. So elbow method is telling us that the k is equal to 3 is the optimal number of k. And you can see the inertia is decreased drastically from 1 to 3. And that's it. We actually created a very good k-mean model in order to cluster our data, and also evaluated it visually and also with a for loop that we created. And that's it.
This will bring us to the end of this course. I hope you enjoyed it, and if you have any questions, you can ask it in the comment section. And also, don't forget to subscribe to my channel for similar contents, and also liking the video to support the channel. Thanks.